You're muted.
Welcome to the fourth day of our Topological Matter conference. Today we have, again, a set of outstanding speakers. We have two sessions, a morning session with Lawrence Molenkamp, Yoshinori Tokura, and Yanon Wang. This will be chaired by Romain Giraud. Then we have an afternoon session with Anna Isaeva, Jagadish Mudera, and Henrik Bettman. Remember that you can ask your questions by clicking the corresponding icons that you will see at the bottom of the screen, either by raising your hand, and then the chair will tell you when to speak, or by typing in the question and answer window. And then either will be read by the chair or will be given the microphone so that you can read it yourself. Also remember that at the end of each sessions, there will be a link in the chat so that you can go to informal discussions with the speakers. For example, here we will put at the end of Hendrik's talk a link for Anna, for Jagadish, for Hendrik, so that you can go and directly talk with them and have informal discussions or questions that were remaining from the sessions. Finally, we will also send an email to those that are registered with the links. So if you leave this window, you will and go, for example, to Anna's talk, to Anna's discussion, then you will lose the links from the other two. So we'll send you make sure to copy the links before leaving or take them from the email. By the end of the conference, we will make some closing remarks, and then the co-chair of this conference, Thanasis Dimoles, will make an announcement of the next Topological Matter conference that will happen in 2022 in Greece, and he will show you some slides regarding to this event. So with this, I'd like to welcome Romain, who will introduce the next speakers of the sessions. In a few minutes, Lawrence will post his talk. So, thank you. Enjoy.
Okay. So hi everybody. Welcome to all participants. And before I start, I would like to thank our colleague, the organizer, for the great organization and give a very successful conference. And thank you, Sergio, for doing a part of my job. So I don't have to remind you that you can ask a question on the question and answer box during the talk, or raise your question at the end of the talk. So my name is Romain Giraud. I'm a French CNRS researcher in the Topological Speedphonic group at SpeedTech Laboratory in Grenoble, and I will chair this morning session. We have three very interesting talks again this morning. Our first speaker is Professor Lawrence Molenkamp from Würzburg University. You certainly know his seminal paper on the discovery on the quantum spin hole insulators. And today, he will show how to turn these helical spin states in a quantum spin hole insulator into chiral edge states by adding magnetic impurities in 2,6 naturally telluride phase heterostructures. So welcome and thank you. Lawrence, please, you can start sharing your screen and give your presentation.
Thank you, Romain. You were actually in sound a bit slipping for me every now and then, so I hope we can fix this. This should be my screen. Is everybody seeing this? Romain?
Yes.
Yes? Okay. So I guess I can more or less start then.
We can see it.
Yep. You also see my laser pointer moving around?
Perfectly moving.
Good. The things I've seen with Zoom, but this seems to be working. Okay, so thanks for the introduction. Yeah, you see from the title of my talk, this is about dilute magnetic topological insulators. We've been working on this. What I intend to talk about is not ferromagnetic material like the BST. This is because we are collaborating with many of the the people here, the TOCA consortium in matters of VBST. What I'm hinting at here is what happens to mercury telluride when you add magnetic impurities. And mercury telluride is a 2,6 material. And as you may know, if you add manganese to 2,6s, they don't go ferromagnetic, but you get some peculiar magnetic effects, and those are the effects that we will discuss in this talk here. So it's something else than the stuff we do for TOCA. My affiliation still is the same. I just can announce that officially today they finished a new institute here at Würzburg where we'll be moving all our equipment to over the coming months, where we can actually hope to expand and grow our MBE samples in better clean room environments. Okay, for the talk. This is actually a reminder of where we come from. And this is already what many of you know. This is the paper in 2007 where we saw conductance quantization in mercury telluride quantum wells that had a inverted band structure. You see the quantization here. And this was the cover of Science that actually announced this discovery. And looking at this, I'm still reminded of how difficult it was to convince the designer of this drawing to actually have arrows on these electrons symbolizing the spins. We wanted them to go through the balls, and somehow that never worked out. But this picture we've seen before. A bit of what's behind this I need to share with you again. So mercury telluride as a material has a inverted band structure. That means that the gamma 6, which usually is the conduction band in zinc blended semiconductors, actually is lowered in energy with respect to the gamma 8, which usually is the heavy hole light hole valence band duplet. And the reason is not spin orbit coupling. The reason is that mercury is very heavy, and because of this you get a relativistic effect, simply the relativistic energy correction that lowers the gamma 6 energy to below the gamma 8. And no spin orbit coupling involved because this is an S state. So you have this inverted band structure, which actually means that, as we know now, that you will have a surface state on this material, the topological surface state. If you start adding cadmium, you reduce this relativistic effect. So this barrier material, which we typically use, has a normal band structure, and that means that you have this staggered configuration of the band edges in your material, and that allows you to actually tune the states in your quantum well with the width of your quantum well. So you have this type 3 quantum well, the staggered quantum well. And now if the quantum well is very wide, the confinement energy is small, and that means that the state that's coming from the confinement of your gamma 6 state is in wide quantum well still below the state that comes from your gamma 8 state. And this is the nomenclature we use. Gamma 6 is normally an electron band, so we call this an E state. And this guy is inverted. And then if you add confinement energy simply by squeezing the width of your quantum well, you push the E state above the H state, and you can have a normal band structure. So that's how we first got into these topological two-dimensional materials. Now, of course, this was done in collaboration with the Stanford group, and the Stanford group actually showed how this could work. And they started out with something called the B8Z model, which was the right simplification of the band structure of the mercury telluride to actually show that you can really have a Dirac mass which goes to 0 at this critical thickness, and that you have this inverted situation. So this B8Z model is only a very good approximation of the band structure if you are very close to this inversion point. So here at 7 nanometers probably still fine. But experimentally, what you prefer to work with is actually quantum wells that are a bit wider, because then you're for certain that you are in the topological regime, to be honest. Now, in these wider quantum wells, there is an extra feature that's totally neglected in the BHC model, but that we see popping up very, very often in our experiments on these quantum wells, which are these peaks here, which we call camelback because there's two peaks. They are simply coming from the hybridization. You have band inversion, so you have these two parabola that you actually pull through each other, and at the crossing points you can have hybridization, and that usually gives you these local peaks which have a bending in the dispersion, and because of this bending you get a very large density of states here. This is a Van Hoven singularity. And of course, anybody who does experiments with gating of materials knows that a Van Hoven singularity does very peculiar things. It will pin your Fermi level when you start gating, and you can get all kinds of extra effects from that. And so this is one of the things that we start to realize is happening in many of our experiments. And sometimes we can use it, sometimes we are a bit upset with it, but it's something that we have to live with. Okay, some other background information from my talk is these two recent studies on lithography. So the original experiments were done in 2007, at the time where we had barely developed nanolithography for mercury telluride. We now know that we've done a lot of things wrong in those days. And one thing is that these samples from those days were made using ion milling, which is very fast and easy to do, but it's also very bad for a very soft material like mercury telluride. With ion milling, you very easily actually eject mercury atoms from your layer, gives you extra doping and all kinds of weird cluster behavior, and they strongly reduce mobility. So you don't want to do that. You really want to go to wet etching, which is a pain, but gives you way better mobilities. I come to that in a second. And the other thing that I also want to mention is the gate training that we've been using. If you scan your gate voltage up and down for a couple of times, this is a trick we borrowed from ferroelectrics. You actually smoothen the potential landscape in your material, and you get a strongly enhanced mean free path for the conductance quantization. So in these 2007 experiments, we had conductance quantization over something like 2 microns. Right now, we have it over 100 micron, and there's no real limit to it apart from material imperfections. Just a bit more to this. This is the wet etching, which we published now a few years ago. The important data is one of them is this graph. You see that if you decrease device size with the ion milled samples, you see that the mobility that you measure in these samples goes down big time. And again, that is from the etching damage that you get in your sample. And you see this affects more strongly in these small samples. The reason is that while you etch, of course, you have a resist on top of your mesa, which means that the top of the mesa and the bulk of your mesa is protected from the damage by the ions. But at the edges, of course, you will have your ions entering your mesa and destructing locally the material. So that's really where your etch channels are, where you're destructing the material. So it's not a good idea to do that. So what you see is that if you actually don't do ion milling anymore, but go for wet etching, and again, wet etching is painful to make nanostructures, but you really have to do it. You get a way better mobility. And the other thing that gets way better is for example, the Hall and Shubnikov-Haas signals. So these are Hall measurements measured from a small mesa, wet etched, and they look just like the big ones. And these are the Hall data you get from the similar mesa dry etched, and you see it's totally reduced. In retrospect, it was a miracle we could see the conductance quantization in 2007. So here's a picture, a SEM picture of these wet etched structures. What you see is that they have very smooth edges now, and the important thing for us also in this SEM picture is that we can actually see the material contrast. The white thing is something that strongly scatters electrons, so that's the mercury. This is the quantum well, which we can see from the side. And we could never see this in ion milled samples simply because of redeposition of the junk that was thrown out of the material by the ions. But you also see here is that in these samples, typically we have way better conductance quantization than we saw previously. So what you see here, this is not on a logarithmic scale, but like we used for the original science paper, this is a linear scale. There's still fluctuations, and they have to do with puddle formation in the interior of your material. We're getting a grip on that, and that's what you can see in this next graph. This is this second paper that I wanted to bring to your attention, the gate training paper. These are actually quite big hall bars, as you can see here. These are longitudinal resistance measurements on hall bars, and what we do here is gate training. And what that means is that you start a gate voltage from a certain value, you sweep up a little bit and go down again. And then you sweep a bit further and go down again, sweep still further and go down again. And what you see is that if you do these training events going from in both directions, what you see is that you will find in all of these samples that there is a minimum rho XX in these samples. And actually the smaller samples you can really push to quantization in this way. And the larger samples, at least you go down in our rho XX in the right direction for conductance quantization. And this is the graph I already alluded to. Now, depending on the size of your hall bar, with your gate training effect, what you do is basically you reduce the puddles that you have in these narrow gap materials, you reduce them big time, and you can really push the mean free path to something like 100 micron. So these are the tricks we use standardly these days, and they really allow us to get reproducible and reliable results in all types of temperature dependent studies. That was the main issue. So what will I be discussing today? I'll have to talk a little bit about what happens to mercury telluride when you alloy with manganese atoms. And then we start applying what we learn from that. So one thing is that we now have observed conductance quantization in manganese doped mercury telluride. That was an open discussion in the beginning. Can manganese doping still sustain a quantum spin Hall effect? Manganese breaks time reversal symmetry. So the original idea is what it couldn't happen. Well, we get quantization. And then we show some more experiments on how these edge channels in these materials behave if you apply a magnetic field. So this is kind of a local time reversal symmetry breaking. This is a global time reversal symmetry breaking. And in these emergent effects, we also see the effects of the camelback for the first time. Then I will discuss the high magnetic field behavior, where again we see very strong effects of ion milling that cause unwanted behavior in some of these quantum wells. And then we see where the time is. I have some more stuff available if necessary. So mercury manganese telluride. Basically, this is what you call a dilute magnetic 2,6 semiconductor. Manganese you can easily dissolve in 2,6 semiconductors because manganese is a 2 itself. So it will simply add to the band structure in the way that cadmium, for example, adds to the band structure. So you will see that there is some admixture of a heavier atom in the dispersion, but it will simply be a 2,6 band structure, a zinc blended band structure. The manganese does not really do anything else. It doesn't make the material ferromagnetic. It doesn't dope your sample because it's a 2. It has these 5d electrons, but these 5d electrons are sitting very tightly in the shell of your material. They have an exchange with the rest of the band structure, but they don't dope. And that means that they also don't induce ferromagnetism to some RKKY mechanism like we know from gallium manganese arsenide, for example. Now you can do this trick for a relatively small percentage of manganese. So what we use here is 1 to 2.5%. You can go higher if you like to, but then you get so much manganese in there that they are seeing each other and they become antiferromagnetically coupled, and that complicates the whole observation. So what we show here is the range where the manganese is typically isolated. And in this range, again, the material is paramagnetic. and so there's zero magnetization in the absence of a magnetic field. But I have this manganese in there, and that of course these are loose spins, paramagnetic spins, and that means that now you can also get a magnetization in the material which comes from these d electrons, which follows simply the Brillouin function for these manganese spins. So the magnetization has this Brillouin behavior, first increasing and then saturating at high magnetic field. And the Brillouin, of course, is for the 5/2 spins because you have D5 in your manganese. The G factor sees the same effect. It follows the magnetization, of course, so you get an enhanced, this is called a giant Zeeman splitting with the same Brillouin function. And finally, this is all for 2,6 the loop magnetic semiconductors. Finally, in our quantum wells with manganese, the density after growth are typically of the order of a few times 10 to the 11. The mobility is somewhat worse, we find, than in mercury telluride. So typically something like 200,000, which is still more than good enough to do decent transport experiments. Okay, so what are the questions? Well, I already alluded to some of these. Can we observe quantized conductance when we add magnetic impurities and break local time reversal symmetry? What happens on the edge channels? Do they survive a global change in time reversal symmetry? And what does this Van Hoven singularity do? So I'll be talking here about 3 devices. And there's an overview here of the actual band structure in these devices. And so this is a diagram showing how this transition between trivial insulator and topological insulator works if you add manganese. This is very similar to what would happen if you add cadmium, say. So already showed in one of the first slides that, of course, a narrow quantum well is a trivial insulator where you have the E1 state above the H1, and for wide quantum wells you have the inverted situation. So these are all topological materials. Now the manganese concentration will influence this region where the material becomes topological. And the other thing is that the width of the quantum well and the amount of manganese also determine how strongly this camelback that I already alluded to start to dominate your hole dispersion. So we work with 3 devices, and they are in the limit where you have a direct TI and an indirect TI, as shown here. And what I mean with the direct TI is that, well, you do have this Kommelsbeck. It's quite presently there, but you still have an extra peak at the gamma point. And so this gap at this point here is smaller than the gap, the indirect gap between the camelback here. So this is what we mean by a direct topological insulator. But if you go further out or add more manganese, sorry, if you go further out, what you will get is situations where actually you have no peak at the gamma point anymore in your dispersion, or have a very small peak sometimes there, and you have an indirect gap dominating your material. So we'll be looking at all of these types of situations. So the first question that we wanted to ask is, what do these magnetic impurities do to destroy the quantum Hall effect? And there have been a couple of predictions in the past about what can happen. And of course, what you're worried about is that the magnetic impurities will cause a spin flip. So a spin in your S channel will scatter off this magnetic impurity. You get a spin flip, and because of that, you get backscattering, and your quantum spin Hall effect is gone. Now there are extreme theoretical ideas about how bad this effect could be. There was this paper by Tanaka et al. Who said actually there's virtually no effect, and the idea here is that well, yes, you can have a spin flip occurring once on a certain magnetic impurity, but it can only occur once, and once the spin is flipped, it cannot flip back. And because of that, if you do a steady state experiment, there is no real effect on the conductivity. The other extreme is by Altshuler, who actually allows a relaxation of the spin of your impurities. And if you then have strong interaction, Altshuler predicted that there's Anderson localization. Now, before these two extremes, there was another paper by Joseph Matsaiko and Sucheng Zheng, the group we collaborated with, actually saying, well, the effect need not be that strong. What you can get is condo singlet formation in your edge channels. And if you have that at the lowest possible temperatures, actually there should be no effect. But yeah, at somewhat higher temperatures, if there's enough relaxation of your manganese spins, you should see a suppression of the conductance. So that's what we set out to see. And here you already see the result of the experiment. This is a small device, wet etched. And we had to do gate training to really get a decent quantization. But what you see here is very clearly a conductance quantization in these samples. And I should add, you can tell, at least I can tell from the the very detailed structure here, that this is a millikelvin experiment. This is 20 millikelvin, 30 millikelvin, something like that. And we see conductance quantization here. We also see the fluctuations are pretty reproducible. So you train once or twice. After training, the fluctuations are reproducible. And you see the conductance quantization both in conductance and in resistance, of course. So what you also see is that the plateau is very long. At least this is for our taste very long. It's 0.3 volts in gate voltage. It's way longer than in samples without manganese, and this has to do with the camelback that actually is eating up a lot of the charge that you put into the sample. So we get conductance quantization. How does it go as a function of temperature? Well, that's in this graph here. Which is the temperature behavior of the gate scan through the gap. So one thing you see is that if you go to higher temperatures, you very rapidly see that the length of the plateau is reducing big time. And again, I'll show in a second, that has to do with the fact that the camelback is playing a major role in carriers, in trapping carriers in your material. The other thing is that the conductance quantization I showed you actually is only good at these really 20 millikelvin like temperatures. If you go to somewhat higher temperatures, you see that actually the conductance is reduced. So this looks like backscattering. So this already starts to look like this model where condo singlet formation actually recuperates the conductance quantization, might have something to it. So a bit more detail first on the length of the plateau. This is a calculation we've done on the density of states in these materials. And what you see is that with the density of states we get from a simple K.P calculation, if you assume that the carriers in the camel's back are basically localized, and the mass is enormous, so they are basically localized at these millikelvin temperatures. We also have independent evidence of that, and that they can be released also into the conduction band by slightly higher the temperature. You predict already from this theory and simple Boltzmann modeling that you indeed get an enormous decrease of the width of your plateau as a function of temperature. And so that's basically explaining what we see here in the width of the plateau. It also means that if you want to really characterize the conductance in the plateau, of course you should limit yourself to the region here where you are in the plateau region and not in the region where you have thermal activation. So that's what we're doing. And so this is the region where we actually confine ourselves to when we plot this average conductance that we measure through the gap. You see the same data here again. But what I can add now is that we can compare this experimental data that we have with the theory of the Zhang group from 2009. And basically they indicated that if the interaction between your impurity and your edge channels is not too strong, they predicted that you would get condor singlet formation at the lowest possible temperatures, which would lead to a recupulation of the conductance quantization. If you have too strong an interaction, then they also predicted that you would get localization. So this goes down, the conductance, if you come from low temperature. Then you will approach the condo temperature, where you can have this correlated effect. And above the condo temperature, you should slowly be increasing in conductance again towards conductance quantization as the condo effect goes away. Now, this latter effect we cannot see simply because at these temperatures above 10 Kelvin, we have across the gap excitation. So we cannot really see the recuperation anymore. But we do observe a very clear condo temperature, and from fitting our data, the red line really is a fit to our data using the theory here, the theoretical expression of Batsaiko. We can really fit our data nicely with a condo temperature of something like 4 Kelvin and an interaction parameter of 0.5. And the nice thing is that this parameter of 0.5 is also what you get if you evaluate this expression with some typical parameters describing the behavior of the material. So it really looks as if this first theoretical prediction on condo effects really was spot on in predicting how manganese impurities will affect the quantum spin Hall effect. So that was local time reversal symmetry breaking. What will a magnetic field do? Let's have a look. This is the same sample. And now we measure both rho XX and RXX and RXY in this sample as a function of perpendicular magnetic field. And what you see is that, well, you get some fluctuations. This is a very small sample, and so you can get some ballistic stuff going around the edges of your sample. But the overall picture actually is really clear. So you come from conductance quantization at zero magnetic field. Rho XX goes to 0 at finite B fields, already pretty low B fields. And at the same B fields, and that, which is about, well, 0.2 Tesla here, you see the development of a quantum Hall -1 plateau in rho XY. So that's what's happening. So somehow something is happening to these states. These is a very low field, of course, for quantum Hall quantization. And of course, the suspicion directly is that this may have something to do with these quantum spin Hall edge channels. To study this in more detail, we actually went to larger samples. But the physics is all very much the same. So this is a big Hall bar, macroscopic Hall bar, with slightly different band structure. It's one of these devices that I showed in the first dispersion plot. So what you see here is for V gate is 0. This is rho XX as a function of gate. So this is in the middle of the gap for this big material. You see the same effects. Rho XX goes to 0, and we have a -1 quantum Hall plateau in this sample at something like 85 millitesla. Now I should add that this is a big sample, so it's too big for us to see conductance quantization at zero magnetic field. That we only see then normally in something like, well, factor of 5 smaller than this one. But the effect is clear again. We see this -1 plateau at a very low perpendicular magnetic field. Now, we kind of had expected to see something like this, and that is because of another very early prediction that I'll show in a second on the quantum anomalous Hall effect. To show a bit more how we can squeeze this -1 plateau onset, if you play a bit with gate voltage, and you saw the gate scan, so if you just vary your gate voltage slightly, you go to the valence band, you see that we can actually have this -1 plateau starting at fields as low as 50 millitesla. So that's basically almost zero field, which of course is interesting for certain applications. Now, the reason we kind of expected this thing to happen is a paper, again, from Suchiang's group from 2008, where they actually, this was the first prediction of the quantum anomalous Hall effect. The idea was, well, we cannot get any quantum anomalous Hall effect at zero field in mercury manganese telluride because it's not a ferromagnet. But if you look at a band inversion in your material, so you have the H1 state above the E1 state, and you now start applying a magnetic field, of course you get spin splitting, and the G factor for these two H and E1 states have opposite signs. And that means that actually if you apply this perpendicular magnetic field and you have this large G factor of the order of 20, what you will get at a given moment is that the band inversion for one spin direction gets undone. And for the other one, you get a even larger inversion. And that would mean that yes, for this one spin direction, this spin up direction, you don't see an S channel anymore, and you're left with a single, which now a chiral S channel for the spin down state in this case. So this was the original prediction for the quantum anomalous Hall effect at the time. We did not know anything about chromium or vanadium doping in BST. But this is actually what we hope to see, and we had, of course, already at that time seen low field quantum Hall effects in mercury manganese telluride and mercury telluride. So we thought this might have to do with it. But the problem is if you really work out the details, you just don't get things to fit very nicely. So what you need in terms of fields to get this situation happening is something like half a Tesla to actually get this crossing going. Now, what we observe in our samples is the crossing somewhere occurring at well 0.5, 0.05 or 0.1 Tesla, which is a way smaller magnetization than what we estimated we would need to get the quantum anomalous Hall effect. So basically, we see our quantum Hall plateau at lower fields than what we expected for the quantum anomalous Hall effect. And that's where we figured, well, we should, the mechanism is not quite the same thing as what Chao-Ching Liu predicted. So we had to look at our KLP band structure again. So here you see actually what's really happening. So what you have here, this is a KLP calculation done by Wouter Beugeling in our group on a strip. So where we get so this is a lattice model, a finite lattice on a finite strip, where we both get the bulk band structure and the S channels in our material. And what you see here in a color code is the location of the various states that we have in our sample. And so you can see that the red and the blue states are the S channels on either side of the sample. And that's the other observation is that you see many of these states here in a conduction band. That is because that's a finite size effect. We cannot really make these samples in our calculations small enough not to see the lateral quantization. But anyway, this is the zero field situation. And at zero field in the band structure that we have in our material now, the Dirac point is just above the Campbell spec. And actually this is a anti-crossing in our calculation, again, because of the finite size effect we have in these calculations. But what happens in this calculation to this band crossing at finite perpendicular fields is the important thing. What you see is that actually the spin states that you have degenerate here, actually one of the spin states of course has to go up with magnetic field and the other one has to go down. And what happens is that both of these spin states are actually leaving the gap. But the important thing is that there's one spin state that actually is shifts down towards the valence band, and there it sees an enormous density of states because of the presence of this camelback here. So what you will have here is that this single spin channel hybridizes away, but the other spin channel actually moves up and it kind of gets into the conduction band, but the density of states is still very low there. So that means that that spin state is still existing. And so this is kind of the mechanism. We lose one of the spin states, but already at way lower magnetic field due to hybridization with the camelback in the valence band. And that's giving us this very low quantum Hall plateau. Now, what happens at gate voltages a bit more into the valence band than what I just showed? What I just showed was all with the gate voltage really in the gap of the material. If you go to slightly larger gate voltages, I'll show you in a second what that looks like. You no longer see a direct transition to an n equals -1 quantum Hall plateau. What instead you see is a series of states, actually a whole series of quantum Hall states going from 5 to -1. And it depends on gate voltage a little bit, but you see that we have Hall quantization that feels actually as low as 20 millitesla now, but this is then a couple of chiral edge channels. So what's happening here is that we are actually with the gate voltage now in the range hitting the valence band. And of course, where you hit the valence band, you also hit the camelback in these samples. That means you don't really move your Fermi level anymore. But this sample is a type 1 sample. And that means that what I'm doing now when I add gate voltage is I add more and more of these localized holes in my my camelback. But I'm not doing very much to the density of states in the gamma point, which has a much lower mass. So what I get is these guys here in the camel's back, they kind of screen away all kinds of imperfections, and I have a very low density holes in my at the gamma point, which can make up my my quantum Hall effect. That's correct is something you can see here, which actually is this measurement of the Hall voltage for these various gate voltages at still lower fields. So what you can get from this is the density that gives you the p-type quantum Hall effect. And you see the density is very low, and at the same time we know from measurements in the N regime that the gate efficiency is way should give you way larger densities, 2 orders of magnitude larger densities than what you get from the Hall effect. So all of these carriers that you put on your gate are basically stuck in the camel's back and are actively screening away all kinds of impurities that the potential might impose on these few carriers in the gamma point. And that gives rise to a very high mobility for these holes. At least this is something we found very impressive in this material here. At these low densities, we have mobilities up to 1 million for holes in our material. And those very mobile holes at the gamma point are, of course, giving us the quantum Hall effect. Now, already alluded that this might be interesting. So one of the things that's ongoing in the literature is this thing about flying Majoranas, mobile Majoranas, and how you could do quantum computing with them. There have been reports on actually contacting these Majorana modes with a superconductor in a BST quantum anomalous Hall structure. Some other people, myself included, actually disagree with that observation. So we had another paper in Science. Actually, the observation in the first paper has changed data axis. And what we can show is that actually in this vanadium dope BST compound and in the gradient chromium dope BST compound, you do not induce superconductivity in quantum Hall edge channels. Basically, you're just splitting up your sample. So everybody is still looking for superconductivity in quantum Hall edge channels, and we think that the system that we have here might be an excellent one to do just that. Okay, so now we have this very early n-1 plateau. What would happen now if we increase the field? Typically what you expect is nothing will happen. So you will simply follow the -1 plateau up to very high fields, and then perhaps at some field you get magnetic freeze out. But to be honest, we have not been able to reach this freeze out in any decent sample yet. So nothing should happen. But what does happen is the following. Very surprising. At 0 gate voltage here, this is the same wafer that I just showed the n=1 plateau. You see that occurring here. You go to fields above something like 5 Tesla. And what you see is that the plateau actually is left behind in RXY, where you get a kind of a shaky curve. Again, this is not noise. This is really what the sample gives you. It's fluctuating the resistance, but it's reproducible. And it's going up very slowly and reaching an n=1 plateau. Now that's weird. At the same time, if you look at the same sample, you can also look at ρxx. What you see is that in this transition, during this transition, you see a conductance quantization at 2e²/h. Now that reminds you of these helical edge channels that we have in the quantum spin Hall effect. And actually that reminiscence is even stronger if you now vary the gate voltage a little bit. What you see for different gate voltages is that you can influence the magnetic field when you transition between -1 and +1. But for all of these cases, you see a longitudinal conductance of 2e²/h. So that could be a single chiral edge channel going somewhere. It also could be counter-propagating edge channels like in the quantum spin Hall effect.
Lorenz, can you please take 5 minutes more?
Sure.
Thank you.
So if you then take the same sample, so I was just indicating we might have a chiral edge channel, we might also have helical edge channels. What you can do is a non-local measurement on the same sample, where you now push the current between 1 and 6 and look at the non-local signals here, this one, 4, 5, and 3, 5. What you see is that also these guys are quantized. Somewhere 1/3 e²/h over e² and 1/6 h over e². Now, these signals we can also understand from a Landauer-Büttiker picture if we have edge channels in there, but only if we have counter-propagating helical edge channels in this sample at these fields here. So what's going on there? How can we have a -1 and a +1 like response at the same time from our edge channels? That there's something weird is also very apparent from the experimental Venn diagram that you can make from your quantum Hall data. What you see here is the experimental Venn diagram, which simply is the voltage derivative of the Hall conductivity. And what you should see is all Landau levels, and you see this works nicely for the conduction band. But in the valence band, again, here we directly go from -1 to +1. And this is really different from what happens in a theoretical calculation of the one such you should do. So what you really should get is a transition between -1 and 0 and +1. What you do see from the theoretical calculation is that, hey, this transition occurs more or less at these fields here, where this star is, and these fields are actually where the 0 Landau levels said. There's one for spin up coming from the conduction band, one for spin down coming from the valence band in these materials, and they cross at a finite field. This is also something we knew for a while. They cross at a finite field, and there the sample is no longer topological. So somehow this transition between -1 and +1 happens at fields where exactly the sample becomes no longer topological. It becomes trivial, field induced. So that, and combining this information with what we knew about dry etching and damaging the sample at the edges of the sample, actually gave us a model that we now think is going on in these samples. So if you have extra damage, you get puddles at the edges of your material. So your Landau level or the potential profile seen by the carriers in the sample should look something like this here and not like flat Landau levels that you have in an ideal calculation. So you get preferential damage at the edges of your sample. So now we can build a story, and that is what we think is happening. So at very low fields, we have this topological -1 edge channel, which still exists in our sample because the sample is topological, and we described how this comes about. But we have strong puddles at the edges of the sample because of the damage due to the dry edging. Now, at this field where actually we get a crossing of these two zero Landau levels, the topological edge channel will disappear. But what you can have now is kind of a percolating, still p-type, but now counter-propagating edge channel along the insides of these puddles. And this one, because it goes in the opposite direction of the edge channels the edge channel that we had previously, looks as if you see a +1 quantum Hall state. So this means that this sample only sees the -1 to +1 transition due to fabrication damage. And of course, the way we know now to get around this fabrication damage is simply to use wet etching. And that's what we do in the next slide. And here you see this experiment.
Lawrence, sorry to interrupt you. Could you please go to the conclusion soon?
This is the one but last slide, please, Roman.
Oh, very good.
What you see here is what happens if you compare dry edge samples and wet edge samples. And what you see in the dry edge samples is what I just showed you. You go directly in your sigma xy from -1 to +1. But if you wet etch the same material, you see, if my laser pointer is behaving, you see now simply a zero plateau for the fields where you actually expect to see a zero plateau. So the -1 to +1 transition is kind of an artifact simply due to the ion milling that you do to your sample. And this explains some kind of worrying observations that our Stanford colleagues reported in 2015, that they also saw no edge channel, and there were some suggestions that the edge channels that we had in our material were trivial and not of topological origin. So we now know that our Stanford friends actually fried the samples, over etched, and actually caused the observation of these puddle-induced situations. So I don't want to slow this here. I will go to the final slide. Basically, what I've showed you is the effects of manganese and some other etching peculiarities on the transport in our materials. So we see a Kondo screening induced quantum spin Hall effect at very small fields. We see that the edge channels will survive magnetic fields simply because they are allowed to hybridize with bulk states and turn from helical into chiral edge channels. And because of that, we see very low field quantum Hall effects. And we understand finally the -1 to +1 transition as due to fabrication damage. There's more effects of manganese in mercury telluride, but that's only in 3D bulk materials, and that's for next year's talk. Thank you.
Thank you very much, Lawrence, for this very interesting talk. Now the session is open for discussion. So I think you can better hear me now.
Yep.
But I have lost now the video, but it's okay. So we have two questions on the chat. If you can hear me, then I will read. The first one is from Vahid Sasgari. He's asking, is this gate training needed because of the gate electrode dielectric interface state or capture charges?
Well, a bit of both. What we think is that so what we need to use in these materials is a gate dielectric, because you cannot really gate the 2 6s with a Schottky. So these oxides, of course, are never perfectly fitting to the lattice, so you will have local imperfections. So you get indeed imperfections at the interface that you can screen away. But I think the major effect is not so much the interface in our case. The major effect simply is that we are in a narrow gap material. Puddle formation is something that happens in all narrow gap materials. If you locally have some doping, the material very easily gets locally N-type, locally P-type, and that's basically what's going on. And what you do with the training, of course, is you flush some carriers in and out of these puddles, and somehow the potential smooths up a little bit.
If I may just add to this question, so it means this gate training, you do the same for independent of the manganese content.
Yes, you can do it for all types of samples. Yes. Now I should add it. Yeah, so we do it for. So what I first showed is that we first found this in non-manganese containing materials, but it also works in manganese containing materials.
Okay, thanks. We have a second question from Ramesh Tamankar. He's asking, how do you make sure that these samples are absolutely clean? I understand that you grow this in UHV, but still I would guess that there are defects, process induced. Do these defects affect your measurements?
Yeah, well, this is a peculiarity of mercury telluride. So we do MBE growth, and MBE is more than CVD. I would say that. Typically, mercury telluride does not want to be doped. And many of these materials that you grow in MBE have a preferential doping. And also many of these topological materials, they all want to be either N or P type. Mercury telluride, and this is for chemical reasons, is the only exception to the rule. It does not want to be doped. So that means I don't have any impurities in there because they're simply grown out of the material. So there are basically very few defects in these materials. There are growth defects. That's what we get. We get dislocations. It's mainly because the substrates are not as good as what you can get for gallium arsenide. And these defects, in the end, the growth defects will limit our mobility. So what we see in our samples, if we're lucky, we can get up to 2-3 million mobility, but more typical, the quantum wells without manganese have something like 400,000 mobility.
Okay, thank you. We have a third question from Young Ha. I don't see the full name, but so this participant is asking, it seems that for wet edge sample, the -1 channel happens at higher B than for dry edge sample. Why? Why is the +1 channel at high B noisy?
So the last one is easier to answer because this is a percolation phenomenon. So really, this other edge channel has to percolate along the inner edge of the damage that is occurring by the dry etching. So this is a process that actually relies on interference, constructive and destructive interference along this rough edge, and that gives you these fluctuations. It's not noise; it's quantum interference. If it happens at higher field, I have not noticed it. Let me have a look at my at the picture. I don't really see it. Romain is typing an answer.
Yeah, sorry, trying to see if there are some more questions. So I'm just checking the chat. Yes, so apparently there are no more questions. Maybe if I may, I can ask one or two more.
Sure, go ahead. There's Juan Sierra raising a hand, I noticed.
Oh, okay.
Yes. Yeah. Can you hear me?
Yes.
Okay. Thanks, Lawrence, for the very nice talk. So Juan Sierra from ICM2 Barcelona. So I have a curiosity. So the emergence of these quantum Hall states at low magnetic fields. So you apply the magnetic field out of plane, so perpendicular. So I'm wondering what's happened when you tilt the magnetic field. Can you
you can get some effects, and this really has to do whether you want to look at orbital or Zeeman effects. I mean, that's actually in the paper that I quoted. So we have a full set of data with in-plane fields, and it allows you to actually determine what G factor is important, the orbital one, so the Zeeman one,
Okay.
or the orbital one, and that's all consistent with the way that we do our KLP calculations.
Okay. Thank you.
You're welcome.
Okay, so we have another question from Carmen Gomez. Can you please unmute the microphone, thanks?
Hello, can you hear me?
Yep. Now I
okay.
can. Yep.
Yeah, thank you for your talk. It was very nice. I wanted to ask you, how do you measure the manganese concentration on your MB heterostructures?
That's a good question. Well, A, we measure flux in our MBE, and B, you can measure magnetization in a thicker wafer for calibration purposes. You can do Raman,
Okay.
and you can do infrared luminescence.
Okay. And how
out
do you?
Of that,
sorry.
Out of that, you work out a calibration curve. So it's kind of painful, but you can do it.
Yeah. And how do you measure your fluxes on the MB? Do you have a crystal quartz, or do you have?
Yeah, this is a quartz. This is a quartz cell.
Okay. Thank you very much.
Yep.
Thank you.
You're welcome.
So apparently there are no more questions. So maybe I have a very short last one. So you're showing a strategy to start from the quantum pinhole states. Usually they have a rather small gap, and then of course the Zeeman with the giant Zeeman effect, then you can inverse this synchronized gap for only one state. The question is, if we would consider system with a larger quantum pinhole gap, would this still work? Because in principle, you need really giant, or you would need a much larger field simply to reach the same state.
You would probably have so. Yeah, if the inversion at a quantum spin hall, is that what you mean by gap? If that's larger, then of course you need a larger field. Yeah. So here you're kind of helped if you want to see the effect at low fields by having a small inversion. So you could tweak for it, but of course the issue is always tweaking these quantum wells is hit and miss, to be honest. You can aim for 7 nanometers and you will get 7.0 plus or minus 0.5 nanometers, something like that.
Okay, thank you. So apparently I missed another raised hand. So Ivan, can I ask his question, please?
Hi, thank you very much for the talk. I have a question about the part of this state that you generate in the edge due to the dry etching. So I wonder if I was just looking at the slides that you present to us, and I wonder if you can get rid of them if you play with the backgates. I mean,
not enough. Basically, what happens is so these puddles, we know a bit more about them. So what happens with dry etching is that you kick out mercury out of your material, and locally, and a mercury vacancy actually acts as a acceptor. So what really happens is that you locally create a lot of holes at the edges, and we have not been able to actually get rid of only those by any gating action. Backgating is another issue in these materials. There is not so much backgating possible unless you grow on gallium arsenide. But if you grow on gallium arsenide, the substrates that we can get for these materials are cadmium telluride, and we cannot get them doped. So if you want a backgate, you have to grow on gallium arsenide. It gives you a big lattice mismatch, which gives you imperfections and also stuff that screens away your backgate. So there is some backgating, but it's not that great.
okay. Thank you very much.
So thank you very much again, Lawrence, for all these very nice, interesting results in the discussion. I think we should move on to the next speaker.
Okay, thank you. Bye-bye.
So the next speaker will be Professor Yoshinori Tokura. from Tokyo University, and he's also the director of the Center for Emergence Matter Science at FICAN. And he's famous for his many contributions in different fields of physics, but today he will present his most recent results obtained with helical spin magnets. And
can you hear me?
Yes.
Yeah, okay.
Can you hear me?
Yes, okay. Yeah.
Good. I'm just so saying that, okay, so you will show the results on, I think, a very interesting contribution showing how very curvature-induced inductance can arise in these spinnaker magnets. We are listening to you.
Okay, thank you very much. And good morning, and also good evening from Tokyo. First of all, I would like to thank the organizers for inviting me to this very wonderful conference. So today, I'd like to talk about some emergent electromagnetic phenomena, especially electromagnetic induction in the helical spin magnet. First of all, I'd like to show the two contrasted cases of the Berry curvature or Berry phase in the momentum space and the real space. Then later I'll focus on the real space Berry phase and introduction to the short period helix or small skyrmions in the central symmetric magnet. Then we can emphasize, amplify the topological Hall and Nernst effect of the magnetic skyrmion. That is a representation of the gigantic emergent magnetic field. And also we next discuss about some dynamics of these helix structures that can generate the emergent electric field. It's nothing but origin of the electromagnetic inductions. Okay. These are my collaborators, and we are collaborate with mainly the RIKEN and also University of Tokyo Joint Group, and working with Arimura and the Nagaosa groups, and also I just enjoy the very close collaboration with my young professors and students. Okay. Okay. This is the two contrasting picture of the real space and momentum space Berry curvatures. And as you know, in the momentum space, this kind of the Berry curvature, and if you integrate it over the 2 dimensions, it shows the so-called the Chan numbers. And it can show the quantized anomalous Hall effect, depending on the Chan number of domain structures. But in the case of the real spin phase, we can define this kind of the winding number, so-called the skyrmion numbers, in the real space. Then it's a quantized object is nothing but skyrmions, and it can carry the quantized magnetic flux, depending on these formulas. So actually, the skyrmion is the original concept proposed by nuclear physicist Tony Skyrm, but later, maybe more than 30 years ago, Professor Bogdanov just predicts that there should be a many magnet, symmetry broken many magnet, which can host a magnetic skyrmions. Actually, this was first discovered by the Christian Preiderer and the collaborators by the small angle neutron scattering, and they just observed the lattice structure of the skyrmions on this kind of the chiral crystal structure, manganese silicide. Here, the spin interaction is mostly ferromagnetic, that are due to the emergent symmetry breaking. There is a so-called spin anti-ferromagnetic interaction, anti-symmetric interaction called the Jaruzelski-Moria interaction. So it shows that usually the competition between the two terms just generates some helical spin structure like this. But you see, under the special circumstances, these 3 Q vectors just hybridized with each other. So these triple Q states can generate this kind of the complicated vortex lattice. And but if you scrutinize one vortex, it's nothing but a skyrmion. Skyrmion shows a lattice form in the triangular lattice form, and this lattice form was observed by neutron scattering. But later, to confirm the real topology of this materials system, we also work on the Lorentz transmission electron microscopy, and you see the skamion phase diagram here, where we can observe also the lattice structure, skamion crystal state. And this is a real space image of the vortex structures. And this is not the cartoon, it's a result based on the real observation. Right? The black part, if you scrutinize this one skamion, and the black part is spin moment is just along the normal direction, but it shows there are swirling vortex-like features, and finally at the core it go down. And so if you apply the magnetic field in this helical structure, the stripe phase, then the skamion is generated, and it shows the order that in the triangular lattice. But with further increase of the temperature, the skamion tend to evaporate. But some skamion is trapped in some trapped site. So this is this image, and you see the skamion is not simply this kind of the density wave-like state, but also the skamion just can be present as a particle natures. Okay, in this skamion, we may observe the very large emergent magnetic fields, meaning originally we can define the so-called scalar spin chiralities, and we have 3 mutually canted spin structures. And then the conduction electron hopping on those local spin structures, then they have a couple to the underlying spin textures. Then its spin direction is positively aligned along the local moment direction. Then the hopping wave function, it can gain some phase factors. It's almost equivalent to electron particles, electrons moving within the magnetic field. So it effectively shows the gauge flux of an emergent magnetic field. This emergent magnetic field is in proportion to the solid angle subtended by these 3 spins. So but in the case of the skamion, this the whole entirety, this solid angle is just 4 pi. So skamion is just wrapped the spheres one time. If the spin is gathered, that's the origin. Right? So the 4 pi by divided 4 pi is nothing but a skamion number, integer topological charge. So that means the one flux quanta is carried by the one skamion if the coupling is strong enough. So that means that if the skamion, for example, the one skamion 10 square nanometers, it's a rather dense skamion lattice, we may have, and also the strong coupling limit, we may have a emergent magnetic fields as large as 400 teslas. This emergent magnetic field just behave like a real magnetic field, but the 400 Tesla is very, of course, difficult to realize in the experimental laboratories. So in order to have a very gigantic emergent magnetic field, and later also the emergent electric field, we have to have a rather short period helix or a small size skamions. So this is also may enable to observe some topological quantum Hall effects. Maybe on the first stage, Ingrid just talked about it, right? So in order to realize such a short period or small size skamions, we should make use of the RKKY interaction. It's a conduction electron mediated spin coupling, and maybe the period of the helix is the order of the Fermi wave numbers. So it's usually the 1 to maybe several nanometers. So in that case, we make use of the kind of the magnetic frustrations and using this so-called frustrated lattice, including the triangular lattice, Kagome lattice, or in 3 dimension, the Kagome pyrochroma lattice. So J1, J2, J3, the competing with each others. And sometimes this magnetic frustration will result in the spin liquid state without any long range orders. But in other case, we have a kind of the some period spin helix state or spin density wave state described by Tsuke instability. And in some some special conditions, this also can form the multiple Q namely the Skamion lattice. Now, actually, the recently proposed by Hayami-san or the Motome, Professor Motome, and they have a very strong scenario to observe the multiple Q states in the high symmetric lattice. In addition to the frustrated RKKY interaction, and if you have some kind of the four-spin interaction, higher order interaction, and then we have a very high probability to observe the Skamion lattice structures. So I'm showing that this one such an example. This is the gadolinium palladium silicon intermetallic compound. And you see that this is the central symmetric lattice, but it's a triangular lattice of the Kagome local spin. Then we have a conduction electrons, then the RKKY interactions, and so on. So in that case, we always, in the magnetic ordered state, in the magnetic field and the temperature plane, ordered state, but these are all almost some helix or some density wavelength system. But its period is a very short, 2.4 nanometers. So actually the interesting order is just a minute. Interesting order is just show up relatively low field regions. One is the IC1 phase and IC2. Next is the A phase, so-called the Skamion lattice phase. And both are composed of the triple Q state. So according to the neutron scattering or some, how to say, redundant X-ray scattering, we can identify the triple Q state, but it's almost show the same result. But we assigned one state is endowed with a topological charge, Skamion number 1, but other state is a non-mean. Perhaps the low state is a Meron, anti-Meron state. Maybe we don't touch on this detail issues, but this secondary phase is so-called the Skamion lattice, where we can observe the very large topological Hall effect. And this is the actual Hall effect as a function of the magnetic field. And you can see the some anomalous Hall effect in the high magnetic region, ferromagnetic regions, or also some normal Hall effect. But only around the low field region corresponding to this phase region, we observe the sharp peak. And this exemplified version is shown here. And we see the only A phase region, Skamion lattice phase. We have a rather top flat peak is here, and its magnitude is quite large. And also, when we apply the magnetic field normal to direction, and then we observe almost very flat features. But when we incline the magnetic fields, then it's suddenly the Skamion tend to disappear, and essentially the Hall effect is essentially zero. But on the other magnetic fields, another Chan number Skamion shows up, and then the plus-one state occurs. And this not only show the Hall effect, but also show the large Nernst effect. As you know, the Nernst effect is we observe the transverse voltage drop when we have some this X direction longitudinal temperature gradient present. Then we observe the topological Hall effect of the Skamion lattice, like here, the top flat features defined between the Skamion phases. But corresponding to this one, we have a very similar or gigantic anomalies due to the Nernst effect. So this is one of the very rare observation of the topological Nernst effect there. And if this Hall effect and the Nernst effect is usually connected, related with each other through the knot relation, especially the anomalous Hall and the anomalous Nernst effects in the momentum space pictures. But then we have checked that this relation, whether this relation holds also down this real space spin textures. And for do that, it's a knot relation means that some energy derivative of the Hall effect is correspond to some Nernst conductivity. And then we artificially change the band filling. It's not so usual for this intermetallic system, but we try to dope the silver on the palladium site or dopes are rhodium on the palladium site. It's just neighbors of the periodic tables. Then it corresponds to the electron doping and the hole doping. And as a function of this doping, we observe the rather systematic change of the topological Hall effect. Very importantly, even rather than the pure state, electron doping system, electron doped system show the even larger topological Hall effect. And however, according to the band calculation, we can change this chemical potential change by these doping procedures. And then we just plot the expected slope of the sigma xy, this region, according to the Mott formula. And this is experiment itself is not so easy, but showed a very acceptable agreement between this simple relation and actual observations. And that means maybe, especially the sigma xy topological is as large as 1,000. So it's a rather correspond to the almost one of the largest anomalous Nernst effect. But this is a rather topological Nernst effect. So I think we think that this is a kind of the indication of the description in the momentum space. It also should be necessary for this very short period Skamion systems. Okay, so let me move on to the electric field effect, emergent electric field effect that can enable the emergent inductor or quantum inductors. And by using this kind of the Berry connections, and the Borovic just pioneered kind of this new Maxwell equations, emergent electromagnetism. And namely, as already said, the Berry curvature or emergent magnetic field is given by the rotation A, and this kind of the scalar spin chirality formula can give rise to the Berry curvature or magnetic field. And but electric field is also derived by the time derivative of the Berry connection or vector potential. Then in that case, Borovic showed that this only that some time derivative of the moment can give rise to the electric field. But importantly, that if the skamion is driven by some way, by some temperature gradient or electric current, and then the skamion gains some velocities. In that case, we have some, it just carries the magnetic field. So we should have some emergent electric fields. And this is a cartoon to explain these features. The skamion carries the emergent magnetic field. So if current is flow and electron flow is here, the electron is deflected by this emergent magnetic field. This is nothing but a topological Hall effect. But as a sort of the counteraction of the topological Hall effect, skamion also shows another direction Hall effect. So this is called the skamion Hall effect. But only the skamion moved with a velocity of the v, then its perpendicular direction, we should have some emergent electric field. And actually, this is our recent example of the tracing the motion of the single skamions of the only 100 nanometer skamion. And we just applied a pulse here, and then the electron is flowing from here. Electron flow is from here to here. Then usually the skamion is expected to move along this direction, but due to this Hall effect, skamion shows some also the transverse motion. This is nothing but a skamion Hall effect. In reality, this skamion Hall effect can give us the electric field, emergent electric field, so that this can give us some correction of the topological Hall effect. And this was very nicely demonstrated by the very macroscopic measurement by the Christian Prader and the collaborators as a correction, a change of the topological Hall effect as a function of the current densities. So, here we should emphasize this emergent electric field is not necessarily user static Berry curvatures. It only contains this time derivative. So in that sense, a skyrmion which carries the emergent magnetic field is not necessary. So this is actually proposed by by Naoto Naga authors, and very simple calculations. And he said that maybe even in the case of the helix, the spin transfer or spin orbit torque, anyway, it can drive the spin textures, and the spin texture forms the deformation structures and by the electric current. So this kind of time derivative and actually the spin moment is a dynamically non-coplanar state. So in that case, imagine the electric field along the q direction or current direction is in proportion to the time derivative of the magnetic movement, but also in proportion to the q vector itself. Q vector means the inverse of the helical period. Right? So we need really the short period helix state. So again, I show that this current-induced deformation of the spin textures here. And there are the two variables. The one is that if the AC current is just tend to drive this helix textures, it shows some tilting structure. But on the other hand, also it shows causes some kind of the rotations. Actually, tilting and the rotation is a rather canonical conjugate relations. So but in the case of the rotations, if the skyrmion is this helix is rather unpinned, not depinned, then it means it's kind of the translational motion of this phase. So in the language of the spin density wave or density wave physics, it should be called phase-on excitation. So I'm sure the one examples, and this is a gadolinium lithium aluminum compound. It's a similar to RKKY magnet on the breathing Kagome-like lattice. And in this pictures, we show the magnetic phase diagram, and in plane direction, the magnetic frustration occurs. So that we have a helix state, and also the magnetic fields apply along the shear axis, this direction. And then we have a transverse conical state. And then finally, the only oscillating moment, it's a so-called fan structure. And finally, it's a forcibly aligned ferromagnetic state. But in between that, we have observed some actually skyrmion state. And if we measure this kind of the emergent electromagnetic induction, then it can be measured by the imaginary part of the impedance. Because the inductance signal is this relation, as you know. So the I is since modulated AC modulation, and then it's proportional to the I to pi f Li. So this means V divided by I emergent impedance shows this quantity. And here, for example, we show the magnetic field dependence also as a function of the temperatures. Right? And in this case, this is a small device structure. So the phase diagram is a little bit different, but the lowest field is the helix, skyrmion, and the transverse conical and fan structures. Right? So here the helical structure shows the rather large inductors. Skyrmion is not that large, but still finite. And the transverse conical is again large. And the fan structure is small, and also the paramagnetic state, it almost tends to disappear. Okay. And also, it shows a very strongly nonlinear behaviors, and it's perhaps due to the nonlinear tilting or nonlinear phase of motion of this system. Right? So very nonlinear behavior. So the problem we have to solve is the many still at present. And one thing is, of course, it only occurs in the very low temperatures. But the problem is whether we can increase some operating temperatures or actual TCs. So in that case, not only the purpose for the application, but also important for the fundamental issue is what is the effect of the thermal agitation or fluctuation of this spin system to this emergent electric field generations. So for that purpose, we search for the rather higher TC materials. Again, we make use of the Kagome lattice state. But this one is a gadolinium moment and the conduction electron. Their role is quite distinct. And but we can use some the manganese 3D element making the Kagome lattice. And recently, this compound is also become very famous. Many people are working on that. And actually, interestingly, it shows the magnetic modulation this along the C-axis. But still, even in that case, rather short period screw state is observed. And again, if we apply the magnetic field in plane, this C-axis magnetic modulation is again the helical, transverse, conical, and fan state and ferromagnetic state. And it's very bear the close analogies, although the crystal structure and Q modulation direction is totally different. And even more important is the TC is the order of magnitude change. But still, like this compound, we have a similar helix, transverse, conical. The magnetic field is applied this direction. Then this cycloidal plane turned over. It's a transverse conical state. And then the fan state. Then we also observe this imaginary part of the impedance. Okay. And in that case, maybe in this current density, it's not that large as compared with the spintronic use. But we show the helical region is a rather negative region. And the transverse cortisol is also negative, but near the boundary, it's become positive. And we just plot the contour plot of the inductance signal magnitude. And mostly the helical region, transverse conical helical region show the large signals, and mostly it's negative, but at only high temperatures, it's turned to the positive. But if we scrutinize the very low current regions, then mostly this region is a negative, but we observe the always the positive signals. Although this current is only 1/4, I don't know, maybe 1/8 of the current density, but the signal itself is much smaller. But important is the low current density, the inductance is always positive. So at fixed temperature and changing the current density, and we just scan the magnetic fields, helix, transverse conical, and the ferromagnetic state. And then the ferromagnetic state is eventually the signal is zero as expected, but originally it's minus signals. And but when the current is not so small, then it's turned to the positive region, and this positive, negative to positive change is a change as a function of the current density. And depending on the magnetic field regions, this shows the minus to positive change. This looks quite puzzling, but we, for example, taking example of the 2.5 Tesla data at this point, then we see that this actual inductance value is very small positive and very largely negative, then turn to the largely positive region. And this region is always positive, remains positive. Why such a non-trivial issue occurs in the inductance as a function of the current density excitation? So maybe we come to the tentative conclusions to explain this phenomenon, and it's mostly from the recently reported theories by Kurebayashi and another author. And we have two deformation of the spin. One is a kind of this tilting, right? Spin is just rotating this way. The other is a kind of the spin rotation. It causes some translational of the helix. So it's phase-on degrees. So this tilting deformation always give rise to the positive inductance. But phase-on relaxation, a phase-on excitation is of course it shows us some pinning frequency or some energy gap here. So it's a pinning frequency. It depends on the pinning frequency. If the observation frequency is much lower than the pinning frequency, then according to this resonance structures, the inductance signal become negative. But observation is higher, or pinning is a very the pinning frequency is a very lower. Then again we have a positive inductance. So the inductance signal can be both positive or negative. And maybe intuitively, maybe you can see this graph. The tilting is all as a function of the omega, it's almost constant one until the very high frequency. But in the phase-on signal, it shows some resonance structures as a function of these pinning frequencies. So the pinning frequency is high enough, then it's only positive. But pinning frequency is close to the observation frequency, and then it shows directly feels the phase-on contribution become negative. But with further pinning frequency lowered, then it shows a positive contribution. This might explain that this kind of the reentrant plus minus plus future, and these regions can be interpreted. It is mostly affected this phase-on excitations in the distensive wave state. And we think a J increase is effectively promotes a deepening of this helix state. So the omega pinning is just 10 to decrease with increase of the J. And this is also not only the temperature magnetic field dependence, but also shows some direct measurement using the LCR methods. And you see this is the inductance value itself. And at high temperature region is a positive, and low temperature region is largely negative, but this value is rather large. And for example, let me compare here the conventional inductors and also these quantum inductors. And in the usually the inductor, classical inductor is composed of the inductor coil, and the inductor coil is in proportion to the square of the winding number and cross section. Cross section means that this coil cross section. So that is the reason why we cannot miniaturize the inductor coil. And in your PC and in your portable phone, you have a lot of this coil. That is the reason why you cannot have a very mini PC, mini one. And the S is necessary. But on the contrary, our quantum inductors, emergent inductor, is make use of this kind of the hairy magnet. We can miniaturize the samples, and also it may show sometimes. It's a very nonlinear, but it's very problem. But it shows a very large value sometimes. So the very short, and it's also inversely proportional to the winding, namely the helix pitch, but also inversely in proportion to the cross section. It simply depends on the, let's say, the current density itself. So we think we optimistically that we can miniaturize inductor coil 5 or 6 order magnitude smaller than the ever classic inductors. So the issue to be solved is still many, and one thing is just very divide-like features of this inductor, and the high frequency response is very bad. Sometimes it tends to up to the 10 kilohertz, but still less than 100 kilohertz. So it's very bad. So we don't know what is the origin, but it's perhaps phase-on deepening is also the source of this one. So maybe these are all nonlinear, or the sign change, or the divide-like relaxation, all relate to the phase-on dynamics or phase-on pinning, deepening process. And the next one is maybe we just work on the screws, but also the
Sorry, we are
cycle.
running a bit out of time, so
Yeah, okay, this is
Sorry
the
to-
final,
Thank you.
final, right, and the cycloid features. So this spin transfer torque or spin orbit torque is also at work. So I guess that maybe by using the cycloidal features, that we may extend this emergent electromagnetic induction phenomena to other material or device structures, including the spin orbit torque on the magnetic topological insulators. We already observed this one, and also the heavy metal and magnet spintronics bilayer combinations. And there be many promising material or device structure should be there. Okay, I'll just give my conclusions. And we just realized that topological Hall and the Nearest effect in the rather very large effect in the very small size scattering state realized by the RKKY interaction. And also using such materials, we just observed the emergent electromagnetic induction in chiral magnet. Thank you for your attention.
Thank you very much, Professor Tukura, for this very nice presentation. So the session now is open for discussion. We already have one question on the chat from Danila Amoko. Can you hear me? Because I apparently have some problem with my microphone. So maybe we can unmute the microphone from Danila, and you could ask, please, your question directly.
Mm-hmm.
Otherwise, I can read it. Danila?
Can you read it?
Yes. Danila, you can speak? Yeah, no.
Yeah, okay, yeah.
Okay, so otherwise, I will read it.
Yeah.
So a rather general and basic question. How is
Yes.
the polarity defined for high-Q skyrmonic objects like for a biskyrmion, considering that those are composed by multiple centers?
Can you repeat the question? Polarity?
How is the polarity defined for high-Q skyrmonic object, like for instance a biskyrmion, considering that they are composed by multiple centers?
I'm not talking about the biskyrmion, right? I don't understand the question.
It was a question about clusters of kyrmions. So maybe she will manage to use the microphone like me.
Yeah, sorry.
Maybe if I can ask maybe also a basic question. In this model,
Yes.
is it important that adiabatic transport of spin is considered? Because you are considering, because of course to have a large inductance, you need to have a short magnetic period. And therefore, is this adiabatic condition for spin transport realized for ultra short magnetic detectors?
So actually, I don't understand quite well. And actually, maybe it's I think that some kind of the spin torque is coming from the usually the spin transfer torque or spin orbit torque. But there is almost I think under the strong this short period helix system, no distinction between these two torques, I believe. Is this?
If it's very short time length scale, then it means that the electron spin, they cannot really follow the magnetic evolution at equilibrium. So that was my question. If this has an impact on the result, or if it's having adiabatic or non-adiabatic transport is not important for the result.
Actually, I don't know the answers, but actually that maybe this damping we observed is a very low frequency regions. So it's not directly this kind of the original spin damping, and I think it's rather due to the some related to the corrective motion of the like a phase-on or spin density waves. So it can be very originally the phase-on mode is goes on modes. So the very low frequency in is okay.
We have another question from Juan Sierra. Can you turn on, unmute your microphone, please? Thanks.
Yeah. Okay. Thank you for the presentation. So I have indeed two questions regarding the topological Nernst effect. So the first one is, what is the temperature gradients that you can build up in your in your samples?
The temperature region for
You need a temperature gradient to measure this Nernst effect.
what
are the So what are the temperature gradients that you build up in your system?
Sorry, I don't remember, but I think that this rather low temperature system, I think it's low enough, I guess.
Okay, and then a more basic question is how this topological Nernst effect, the magnitude of this effect, compares to the Nernst effect in conventional ferromagnets.
Yeah, and it rather corresponds to the family of the largest Nernst effect compound. So for example, the topological Hall effect itself is almost 1,000. So it's almost a limit of the intrinsic anomalous Hall effect. So I think the Nernst effect is also as large as some of the maximum magnet group, which show the very large anomalous Nernst effect. Yes.
Okay, thank you.
Yeah. That is the reason why I just emphasize that this result, maybe we just use some discussion based on the real space pictures. But in reality, if the magnetic texture becomes so small, so in that case, we have to move to the maybe case-based pictures. But still, it's not theoretically, it's not so easy. Maybe the many folding occurs in the Moriland zones, and so I think it's very difficult issue. But maybe case-based picture might be better.
Okay. Thank you. Thank you.
Let me thank you, Professor Tokora, for this very interesting presentation. To all participants, you know that you can meet our speakers in these meeting rooms. You have the link in the chat. So I invite you to leave this session now and to join the meeting room if you want to further discuss with our speakers.
Okay, I can just
after the coffee, please. You have also to leave this one and to go to the other one. Are you already in the other one, or you have the link in the chat?
Yes, yeah. Just try to click, right? Okay, once have to.
Hi, Daniela. I'm part of the organization. Do you want to check if your
hi.
audio works?
Yes. Hi. Can you hear me?
Yeah, I can hear you.
Okay. I don't know what's the problem in the general room because I noticed that also other attendees cannot speak during the meeting.
Yeah, sometimes there are issues with that, but yeah, hopefully it works now. So you go ahead. Welcome, Professor Takuya, to this discussion. You're muted at the moment.
So can I?
Oh, hold on, Professor Takuya.
Yes.
Oh, yeah, sorry. Yes, thank you for joining this discussion session. And thank you very much for your talk. I'm part of the organization of the conference.
Oh my God.
Hi, can you hear me?
Yes, we can hear you.
Great.
Is your video also working?
Yeah, I'm trying to switch it on. Okay.
That's perfect. Perfect. Okay. Before I start, I'm sorry to ask you this, but how do I pronounce correctly your first name? Is this Jianong?
Yes, Jianong.
Okay, perfect. Okay, thank you very much.
Okay, so you'll be chair of this
Yes.
session. Okay, thanks.
So, yes, so you will have 35 minutes, yeah?
Yeah, so
you have 30 minutes, so
yeah.
Maybe if you don't mind, after 25 minutes, I just show up and just say that you have 5 minutes left, and then just sure. My duty. So
yeah. So the discussion session during the lunchtime, how long it will last?
So this is probably written in the forum. To check. Yes, I guess it's up to the participants. So
okay,
there is there is a 1 hour and a half pause. I guess you will have time for I don't know, dinner. Yes, I guess just directly after your talk, there will be the questions, and let's say for 5-10 minutes maximum. And then if there are some people being keen on discussing longer with you on specific subject, then you can meet them in a specific room. There will be the link appearing in the chat, and then you would just have to leave this session and to open the Zoom chat for your meeting room.
Yeah, sure, no problem.
Before, because we are just the two of us, so I can maybe already discuss shortly with you. I mean, are you still working on this 3D TI films and proximity effects? Because
well, not exactly. Well, this is a slightly old work, but we're still working on some kind of unconventional superconductors. But for the proximity effect, we're trying to work, but it's kind of device fabrication is quite difficult.
Okay. So you're not explicitly using bismuth selenide, for instance, anymore, or are you still working with bismuth selenide?
We are still using niobium diselenide as a superconductor, but we are not. We're also trying to do the proximity effect in other systems rather than this 3D TI.
Okay. Okay. Thank you.
Because my group is pretty small. So is it time to start?
Already a raised hand. That's good.
So should I start?
Let's wait for 2-3 more minutes.
Oh, okay.
Please. Okay. I see both. Maybe turn. Okay. So I can start. Okay. Good. Let's start the last. So we are happy to welcome as the last speaker Jian Yong Wang. He's a professor at Hong Kong University. Her group is studying magnetotransport and optical properties of 3D TIs and also transition metal diketoogenides. And today she will present her some past work on proximity effects between superconductor and 3 topological insulator. So we are listening to you.
Okay, so thank you. First, I just like to thank the organizer of this conference, gave me this opportunity to introduce some of our past works on superconducting proximity effect in topological insulator and also superconductor hybrid structures. Okay. I'm from Hong Kong University of Science and Technology. This is our kind of campus view, so we have quite a nice view. So before I start, I would like first acknowledge my collaborators in this work. It's from the experimental side. We also collaborating with South Tech Professor Hong Taohe. And for the series simulation is was carried out by my colleagues, Professor Vic, Laos Group. And financial support is from both Hong Kong government and also mainland National Science Foundation. So this will be the outline of today's talk. We'll give a very brief introduction, and then we'll introduce our device structure, and then our major result, both experimentally and numerical simulations. And you will see that we have very good kind of agreement between experiment and also simulations in which we can distinguish surface state associated kind of superconducting proximity effect and also identify the bulk state associated features. So the interest to study superconducting proximity effect is begins with this kind of theoretical work that once we have S-wave superconductor, through the proximity effect, it can induce P-wave superconducting state in topological insulators, which can kind of host Majorana fermion at its vortex. Okay, so and there are numerous kind of studies, both in transport study and also many other techniques to study this hybrid TI and superconductor hybrid structures. Okay, and also in transport, you can observe many interesting features like plateaus and zero bias peak and etc. And more recently, and also this work still going on with different aspects as well. But the problem is that there is many possibilities to explain the experimental observed features. Okay, and so to identify exact physics origin, which is still quite challenging, and also to distinguish topological surface state related proximity effect and also and bulk state is also very important. Okay. So in this work, we use 3D topological insulator between selenide, which is a kind of layered crystal, and which is known as a topological insulator as a surface state. Okay, direct point about 270 MeV below bulk gap. Okay. And the superconductor we employ to use is also a layered crystal, which is a 2H niobium diselenide. Okay, and it has transition superconducting transition temperature about 7 Kelvin. Okay, so basically we just acquire a commercially available kind of a bulk crystal of these both materials, and then we use mechanical exfoliation method to get niobium diselenide flakes and also bismuth selenide flakes, and then through the dry transfer kind of technique, and we build a junction. Okay, so lower niobium in this device, niobium diselenide flake is at the bottom, and bismuth selenide flake is on top. So the overlapping area is highlighted by this purple dashed rectangle. Okay, so basically, if we look at cross section, the structure, device structure is like this. Okay, so with the super. Once the temperatures are below the niobium diselenide TC, and then we'll have a superconductor at bottom and then 3D TI on top. So the proximity effect can induce both superconductivity for the surface state and also the bulk state. So before we measure this device, we also did some transport measurement for the selenide flake, and we can observe this Schopenhauer-Haas oscillation, and from the angle dependence, we know it has 2D nature, and then from the Fan diagram, we know it comes from surface state. So more importantly, from this SDH oscillation, we can determine where the Fermi level lies for our bismuth selenide flakes, okay, which is determined about 270 millielectron volts above Dirac point, and which is just at the minimum of bulk conduction band for bismuth selenide as well. Okay. And so this is a temperature dependent resistance measurement for this device. Okay, so for the kind of large temperature range for this left figure, we can see that there is a sharp resistance drop occur at about 7 Kelvin, which is corresponding to niobium diselenide superconducting transition. And more interestingly is that approaching 2 Kelvin, okay, we seem to see another resistance drop. So we can transfer the device to the dilution fridge. Okay, our small dilution fridge can only work between 4 Kelvin down to 100 millikelvin. Okay, so for the right panel, we can only see the RT in this narrowed kind of a temperature range, and we can see that indeed below 2 Kelvin, we can see another big resistance drop. Okay, so which we believe is corresponding to the superconducting proximity induced the superconductivity bismuth selenide. Okay, and by applying a magnetic field, of course, we can see this transition temperature is just moving to the lower temperature. And then if we look at the magneto resistance dependence, okay, on the field of magnetic field applied, we can also see the two features corresponding to the RT feature. Okay, so when the temperature is lower, we can see a sharp dip around 0 Tesla, and but we can also see another kind of valley, okay, which is in a larger kind of magnetic field range. So basically, we can determine two critical magnetic field, which is corresponding the two transition temperature. Okay. So in order to have more kind of understanding about this superconducting proximity effect, we carry out the differential conductance spectra kind of measurement, okay, across this niobium diselenide and bismuth selenide junction. Okay, and this is TIDV versus voltage applied kind of a spectra. And we can see that there are two striking features. One is kind of conductance plateau. Okay, so this curve are offset just for clarity. So there is a conductance plateau which occurs, okay, at 4 Kelvin we can see plateau only, but once the temperature decreases to 2 Kelvin and below, there is a new feature coming out, which is a zero bias kind of a conductance peak. Okay, so this has two distinguished features, and one corresponding to the second transition temperature around 2 Kelvin. Another, this plateau, we believe, corresponding to the high transition temperature, which is close to the niobium diselenide superconducting transition temperature. Okay. So for the time being, let's focus on the plateau first. So we see as the temperature kind of increase from the 0.5 Kelvin, this plateau width is actually decreasing. But however, the magnitude of the plateau doesn't change very much. Okay. So if we plot the temperature dependence of the width of this conductance plateau, which shown as this black dots, and also together we plot from BCS series plot niobium diselenide kind of gap dependence on the temperature with superconducting transition temperature assumed at 7 Kelvin, which is this right curve. And we can see that our data kind of fade to a lower kind of transition temperature. Okay, so this purple dashed line is corresponding to the TC of 6.5 Kelvin, and this green one is 6 Kelvin. Okay, so this plateau kind of corresponding to the, we believe, okay, is corresponding to the superconducting proximity effect to surface state. Okay, because surface state wave function is more kind of localized at the interface, so it's expected to have a stronger kind of influence by superconducting transition of the niobium diselenide. So, and later I will show you that from our theoretical simulation, and indeed this plateau is coming from the surface state. And now if we closely examine the zero bias conductance peak, okay, which occurs below the 2 Kelvin, and then we find that its peak intensity, okay, is actually decreased with increase in temperature, and its peak width, okay, is increased with the increase of temperature. So this is quite kind of interesting phenomena, which is quite different from other from the plateau kind of situation. So the plateau situation with is decreased with increase in temperature, but here the peak width is increase with increased temperature, so implying that it's kind of thermal effect. Okay. And the width itself is much less than the plateau width. Okay, plateau width is in a kind of order of 2 millivolt, which is fairly close to the in the same order of magnitude of a superconducting gap of niobium diselenide. But for the plateau, it's kind of order of magnitude smaller. It's only around 0.13 millivolt at 0.1 Kelvin, and it also doesn't change too much below 1 Kelvin and start to increase sharply above 1 Kelvin. Okay. So, and then we believe that this because if we associate the plateau to the surface state, and then this zero bias kind of peak may associate it with the bulk state. Okay. So to kind of really understand the physical origin of these two features, we observed experimentally, and we did a numerical simulation. And the simulation system is kind of mimic our experiment. Okay, so this is a case when we assume the temperature is smaller than the second superconducting transition temperature, and the superconductor is kind of connected with a normal metal, and the topological insulator is semi-infinite. Okay, so partially become superconducting, and partially it's a normal kind of topological insulator. So when the current goes through this structure, we will expect to have a Andreev reflection for both surface state, okay, from normal surface state to superconducting surface state, and from normal bulk state to the superconducting bulk state. And so we can actually calculate the DIDV spectra, okay, and to see based on the Andreev reflection. Okay, so this is a calculated result, and in this case, we assume that Fermi level is at 274 milli-electron volt. It just touch the bottom of the bulk conduction band of bismuth selenide. Okay, so this is the surface state, and this is a bulk conduction band, and it's a bulk valence band. And so the differential conductance calculated kind of reproduce what we observed in the experiment, that is a zero bias plateau and also zero bias peak, just like what we observed in the experiment. And in this simulation, we can also change the number of the quantable layer, that is the thickness of the bismuth selenide sample. Okay, as we change the number of quantable layers, and we can see the conductance plateau doesn't change. But however, the zero bias peak is become stronger when the layer number is increased. Okay. So this kind of layer dependence of the zero bias peak, then, and also layer independence of the plateau, kind of indicate that plateau is coming from surface state, and this zero bias peak is associated with the bulk state, because it really depends on the bulk layer kind of thickness. And of course, we can also further verify just by changing the location of the Fermi level. Okay, so we can adjust in the simulation where the Fermi level lies if we adjust it within the bulk gap. And in this case, from the simulation, we can only see the conductance plateau. Okay, and it doesn't depend on the quantable layer number of bismuth selenide. And so this indicates that this plateau indeed coming from the superconducting proximity effect to the topological surface state. And we can also, by changing the tight banding parameter, make this bismuth selenide become trivial. Okay, so there's no surface state, and then we just only look at the case where the Fermi level just lies at the bottom of the conduction band. And in this case, the simulated differential conductance spectra just shows a sharp peak. Okay. So this further simulation just indicating that plateau are indeed, conductance plateau are indeed associated with the surface state, and this zero bias peak is associated with the bulk state superconducting proximity effect. And we can also estimate the gap, okay, induced superconducting gap by kind of plot the spectral dependence. Okay, spectral function of the bismuth kind of selenide. So qualitatively, at normal state, okay, if you look at the Fermi level, the energy spectrum at Fermi level, it will have two circles. One is associated with the surface state, okay, another, which is this larger circle, and another associated with the bulk state, which is this small circle. But once superconducting proximity effect is take action, and then the superconducting gap will start to form, okay? And then for the bulk state, this gap will be much smaller than the surface state, okay? And from this simulation, we can kind of estimate the surface state induced superconducting gap to the surface state is in the kind of about 70% of the gap of niobium diselenide. But for the bulk gap, which is only about 10% of that niobium diselenide. Okay, so this sharp kind of zero bias peak is really associated with a weak kind of superconducting proximity effect and small induced superconducting gap. So we can further study the effect of the Fermi level kind of location. Okay, so if we put the Fermi level deep into the bulk conduction band, okay, in this case, the Fermi circle between the bulk state and the surface state have a kind of a similar size, and then the differential conductance spectra will be completely different, and we can see the sharp zero bias peak has significantly broadened, okay, almost at have the same width as the conductance plateau. Okay. And so this sharp kind of conductance peak is really depends on where the Fermi level is located in the bulk gap. And the experimental observation would also depends on the interface quality. Okay, here we can simulate, okay, with different degree kind of interface transparency, and when the interface is very transparent, okay, we produce a simulation produce a result similar to the experiment. But if we reduce the interface transparency, and then the spectra will also changing. When the transparency is low, basically the zero bias peak will be completely surprised, and also the plateau will become much narrow, okay, and less sharp. Okay, so this kind of indicate that for our device, okay, the interface is very transparent, okay, which enable us to observe these two distinguished features associated with the surface state and the bulk state. And we can also kind of try to explain the zero bias peak kind of broadening effect, okay, and we think it's a thermal effect. So so in this simulation, we use a parameter which is thermal energy, the ratio between thermal energy and the superconducting gap. Okay, so when this parameter increases, and means the thermal effect is also increases, and we can see that zero bias peak intensity is decreased, and the peak width is also become broadened, okay, as it is plotted here. So the the blue shows the width okay, and black one shows the intensity. Okay, so as the temperature increases, that is this ratio alpha T will increase, and then the intensity decrease and the peak width broadens. Okay, so this is also in very good agreement with experiment. Okay, so this is what we observed: a change of the width and change of the intensity, which is different from the case of the plateau, because the gap associated with the surface state is quite large, much larger than the thermal energy. So we won't observe a thermal effect, but the gap induced to the bulk state is much smaller than that of surface state, which the thermal effect become important. Okay, so that's how we can observe the thermal effect of the zero bias peak. And so to summarize, we can simultaneously observe in the experiment a conductance plateau and a zero bias peak, okay, in a differential kind of a conductance spectra. And both features can be very well produced, okay, qualitatively in agreement with theoretical kind of simulation. And from the theoretical simulation and also from the plateau width and zero bias peak width, we can actually estimate the induced superconducting gap. Okay, first identify that plateau is indeed from the surface state and the zero bias peak is from the bulk state, but the corresponding superconducting gap has a kind of order of magnitude difference. Okay, so this kind of experiment shows that it is possible, okay, indeed to use superconducting proximity effect to induce PV superconducting state in the surface state of 3D topological insulator. But then how we can actually utilize this system would be for the future work. Okay, so thank you for your attention.
Good. Thank you very much, Jianrong. So the discussion now is open. So we already have one question. I will switch to also for the chat. So no hand raised. So we have one simple question.
Yes, I wanted to ask whether finally this zero conductance peak is, excuse me.
Yeah.
I didn't see you raise your hand, so I was reading another one, but it's okay, just go on.
I raised my hand, actually.
I see it now.
I'm sorry about that. Should I continue?
Yes, please.
Yeah. So, I wanted to ask whether this zero conductance peak has any relation at all to Andreev reflection, or is some other origin?
Oh, it's due to the Andreev reflection. It's just it's Andreev reflection from the bulk state.
The bulk state, yes. And also the plateau is Andreev reflection from the surface state.
Yes.
Yeah. I see. Okay, thank you very much.
Okay, thank you. So
and yeah, there is a question in the Q&A. Why is the resistance drop? It's only fraction of the R. Yeah, that is mainly because of the device structure. Okay, so if you look at our device structure, we have series resistance. Let me share the screen. Share the screen again. Okay, so in fact, oops. Yeah, if you look at our device structure, there is 3 parts of the resistance. One is from the bismuth selenide flake, Another is from niobium diselenide, and the third part is a interface part. Okay, so what we actually measure, the resistance in the RT kind of measurement, is not just the superconducting part. It also contains the series resistance in bismuth selenide kind of flake. So that is why it won't really kind of drop to the zero resistance.
Are there other questions? So I don't see, or maybe. Yes, we have a question from Juan Sierra. Can you please unmute your microphone?
Okay, thank you for the talk. So I have a curiosity regarding these devices. So when you do the stacking of these two materials, so you just show that you have a clean interface. So do you do some treatments on annealing for cleaning this interface, or?
No, it just we did it in a glove box.
Okay, this was also my second question. Okay, just to in a controlled environment. Okay.
Yeah, we're in a controlled environment, but even in a controlled environment, you cannot always get very transparent.
Exactly. Yeah. Okay. Thank you.
Okay, thank you. Are there other questions? I don't see other question. Maybe I can ask or comments. Just ask a question about. So you show us initially Shumnikov gas oscillation of your sample.
Yeah.
And as far as I remember, you wrote it's like 60 nanometer thick.
Yes.
So normally, because they are highly doped, these bismuth selenide system, so you have a massive amount of bulk carriers, and, and you should have like 3-band transport with a really large density of bulk carriers. So my question is, if you show again this Shumnikov gas oscillation,
okay,
it looks like single band. So I have 2 points. So it looks like single band. And second, it's a very large carrier density. So in the end, when you look at the Landau level fans, it's a very large, it's a large end limit. So here, this looks like really a single band. And then if I look at this curve on the upper right side, if I understand what you say that you extrapolate from your large end data to n equals 0, and you find that it's a 1/2 value, and you attribute this to a topological surface state.
Yeah, there are two reasons. One is this one, it's extrapolated to the negative 0.5. Another is this angle dependence. If we can change the magnetic field, relative magnetic field to the sample surface, and it shows this oscillation has kind of a two-dimensional nature. It depends on the input.
Bulk carriers can also show this kind of angular dependence.
Sorry?
Bulk carriers can also show this kind of angular dependence because you can have a magnetic length.
No, both carrier would not have will have a angle dependence.
So just to finish, so very shortly, we can chat in the discussion afterwards. So it looks like a single band.
Single band.
You have only one type of carrier here in this data. You
have
a very
regular
increase of
Yes.
And from this, you say, okay, you have surface states, but your Fermi energy is at 270 millieV, so it's clearly in the conduction band. So you should have also.
We have electron. Yeah, we only have electron conduction here, but one is in the surface state, one is in the bulk state.
Okay.
But it's the Fermi level is not deep in the bulk conduction band. It's just at the very bottom of the bulk conduction band.
Thank you. Are there other questions from the attendants? I don't see any. In case you want to discuss with our speaker, so there will be the lunch pause, but of course you can meet. So you have the link in the chat. You can meet Professor Wang in the meeting room And
Okay, so
thank you again for your presentation.
Okay, thank you for inviting me. I will just go to the Zoom meeting then.
Zoom link. Bye-bye.
Bye-bye.
Hola, Sergio. ¿Me oyes?
¿Me escuchas? ¿Me escuchas?
Sí, te escucho. A ver. ¿Vuelve?
A ver si me escuchas bien ahora.
Sí, se escucha claro, sí. Si puedes, si tienes algo más de volumen, lo puedes modificar o no.
Espera, espera. ¿Qué tal ahora?
Sí, yo te oigo bien.
¿Se escucha mejor? Le subí bastante más el volumen.
Espera que voy a ponerme los cascos para todo el mundo.
¿Puedes mirar tú en el ordenador?
A ver, dime.
Pues, pues,
A ver, habla.
sí,
Sí.
está escuchando Juan. ¿Se escucha bien?
Perfecto, perfecto.
Ok.
¿Qué estás solo con el del ordenador?
No, estoy con el de la camarita pequeña.
Ah, vale. Vale, pues ahora voy para allá. Gracias.
Hola.
¿Me escuchas, Juan?
Sí, te escucho.
¿Se
Se
escucha
escucha bien. Se escucha bien.
Ok, listo.
Sí, se escucha.
Hi, Sergio.
Hey, how are you?
Hi, fine. And you?
Okay.
Yeah?
Yes.
Nice.
Perfect. Thanks for joining.
Thank you very much for inviting me.
Yeah,
It's very exciting.
So we are already in air, so anyone can hear what we say.
Very
So,
nice.
in any
So
case,
welcome, everyone.
Maya is going to be a chair of your session. She will join soon, I guess. And then what I'm going to do, and well, I could already remove these slides if you want to put yours.
Yes, absolutely. That would be great. So let me start sharing. It says I cannot start while you're sharing. Okay. So here I go. So is it visible now?
Yes, perfect.
Nice. And can you see my pointer?
Yeah, also.
Fantastic.
I think we are all set. Sound is perfect too. So
okay, happy to hear that.
you can leave it. You can leave it there, and from my and then we start exactly at 3.
Sure.
Good. You already talked to Maya. She will connect soon. All right. Thank you.
Thank you. Yeah, Adriana is so we had a technical chair.
Hi, nice to meet you. I'm Adriana.
Hi, I'm also nice to meet you. Yeah, happy to see you.
Yeah. Okay. Hi, Maya.
Hello.
Hi.
Hi, Maya.
Hello. So, okay.
Guess we're still waiting a couple of minutes.
Yes, typically people start connecting exactly at a couple of minutes before the talk. So
yeah, we can. Yes.
No, we are also streaming in YouTube, and the number there also increases.
Yeah, that's a nice idea.
So we wait until the last moment, and then we start at 3 sharp. So you also know that we have these meetings afterwards, and we were gonna post it there on the chat. So go directly to
That's a very good idea. Yes.
Yeah. And then okay, there will be one link for each of the speakers. It will be after Hendrik's talk.
I see. So I cannot use the same link as I use now. I will have to follow the other one.
Exactly. No, you will find a link on the chat, and then you click there. You will need to go out from here, and then if you want to hear the closing of the conference, come back. And in the closing, Thanasis is he's here too, co-chair of the conference, and he will present the next next year. You can see now people are starting connecting. Okay, I go away. You're the focus is on you.
Hi there, Hendrik.
Hi, Anna. Nice to see you.
Nice to see you too.
So,
Hendrik.
hi, Setu. Did you already? Ah, yeah, you have already shared the screen. So.
Look, by using the same low energies over and over again.
Okay, should we start?
It looks like that, right?
Okay, welcome everybody. So the first speaker of the afternoon session is Anna Isaiva from the University of Amsterdam. Anna Isaiva is a world-leading expert in growing these magnetic topological materials based on binary decalcogenides. And today she's going to talk about the intermixing disorder in the intrinsic magnetic topological insulator based on manganese. And as I said, this binary decalcogenide studied by X-ray diffraction and bulk magnetometry. So Anna, please, the word is yours.
Thank you very much, Maya, for the nice introduction. Good afternoon, everyone. Thanks a lot for being here for my talk. I'm very excited that we can finally exchange science and be at this conference 1 year later. So as announced, I will be talking about the intermixing disorder. So I will show you how it can be elucidated, because it's quite a tricky phenomenon in this group of materials. And then I will show by the results of my cooperation partner how does it affect the magnetic properties of these phases. So as it happens, real materials are much more intricate than simple models. And in this class of compounds, there is increasing understanding that the topology is very intimately affected by this intermixing disorder. So let me start by expressing my deepest gratitude to all the wonderful people who are involved in this project. So first of all, the members of my own group who grow the samples despite all the hurdles and then analyze their composition and structure. So this work was mostly done at the University of Dresden, at the Leibniz Institute in Dresden. Therefore, you see the logos here, but recently I've moved to Amsterdam, so I will continue that work. But all I'm showing you today was basically done in Dresden. Many more nice experts from different fields, experimental physics, theoretical chemistry, were involved in this research. So you see the names and some faces here. There will be also a complementary talk later in this afternoon session about the surface spectroscopy of these materials given by Hendrik Bentman. And last but not the least, I would like to also thank very much the group of Evgeny Chulkov, the theoreticians from San Sebastian in Donostia, who gave the impetus for this study, because they made the first theoretical prediction that this manganese bismuth tellurides, bulk periodic compounds, could be intrinsic magnetic topological insulators. So many more people worldwide are nowadays involved into the research of this family. So manganese bismuth telluride 1 to 4 has already been the topic of many articles, exploding from 2019 when the first complementary study on it appeared in Nature. So those of you who attended the tutorial earlier in this conference on Monday given by Mikhail have already learned about these compounds and how important it is to have this out-of-plane ferromagnetic coupling in them, and additional symmetry arising from this fact is taken into account when the topological invariant is calculated. I would also like to point out that these materials are not only predicted to be an interesting platform for quantum anomalous Hall effect, but this effect was actually already observed in thin film of manganese bismuth telluride and published 2020. So leading this theoretical prospects of having intrinsic magnetic topological insulators to fruition. As I said, my group is mostly interested in material science, so materials aspects of these phases, and therefore I will be talking about the, let's say, the base level of this research, how to obtain these materials, how to understand their compositional and structural peculiarities, and how that further perpetuates into their properties and ultimately into their topology. So as we will see, lots of very tiny subtle aspects have to be taken into account. So let me start by a very quick historical survey, so to speak. So extrinsic doping of magnetic TIs is a long-term topic. So already as early as 2010, there were experiments and subsequent theoretical predictions dealing with intercalation of transition metals into the classic topological insulator, the primer bismuth telluride. And manganese back then did not seem like the best choice of a transition metal for doping. So if we look at this experiment here, only at certain concentrations of doping, a ferromagnetic easy access ferromagnet has been observed in this material, and the transition, so the critical temperature was relatively low. Well, it is still quite a bit higher than what was obtained for extrinsically doped heterostructures on bismuth telluride, these chromium-based heterostructures where quantum anomalous Hall effect was observed, but still it was not as striking. So these low expectations for extrinsic manganese doping were further substantiated also by theory that looked at this modeled compound, so manganese taking up some place, so crystallographic positions of bismuth in the structure of bismuth telluride. They calculated that indeed this configuration should show a ferromagnetic ground state, but the resultant magnetic gap at the Dirac point would have been very, very small, so not substantially large to provide robust quantum anomalous Hall effect. Well, some research in that direction has continued, and people started noticing some discrepancies. So let's say the result of this research, a more closer look at the magnetically doped bismuth telluride, has resulted in this very nice paper provided by the Rada group in Berlin, where they looked at the manganese doped bismuth telluride a little bit more closer and noticed that there are not only quantupole layers there that correspond to the well-known structure, tetradimide type structure of bismuth telluride, but there are also subtopole layers there unexpectedly. So the subtopole layers obviously have a different structure. They were also shown to contain manganese. So they were naturally the first candidate to be looked at and the first candidate to probably be responsible for the topological properties of these heterostructures. Even more interestingly, these heterostructures of quantupole and subtopole layers also showed quite larger magnetic gaps than was anticipated by theory for a manganese doped, extrinsically doped bismuth telluride. Further on, people started approaching the subtopole layers from a different side. So 2013, there was a first paper reporting that probably a bulk compound with stoichiometric ratios of manganese and bismuth can exist, and that this compound may be built out of the subtopole layers, exactly the same ones that were observed in this heterostructure. The problem back then was, as reported by the authors of this paper, that the compound seems not to be very stable. All attempts to quench it from the higher temperatures and to get a crystal or somehow characterize its physical properties have failed because it seemed to decompose as the temperature is decreasing. So with all this prior information and thanks to the very fruitful exchange with a group of Mikhail and Yevgeny Chokov, we were very interested to start looking into this material system. And we found indeed that this compound exists, but requires very precise and somehow complex synthetic conditions to be obtained as a single crystal. So it took us some time, so several years after the first publication, but then we succeeded and grew this crystal, giving the access to the elucidation of the physical properties. So let me briefly summarize what we have done on the material side, why it was so challenging. So first of all, when you start synthesizing this compound, you have to deal with the starting materials that have very different melting temperatures. So basically you have solid manganese telluride and you have melt of bismuth telluride that melts almost 500 degrees lower. And then when you grow crystal from this melt, it is a heterogeneous solution. Then, so as one can see from this differential scanning calorimetry data, when you start to crystallize the melt, so we are going down in temperature here, you first hit the crystallization peak of the ternary compound. So this 1 to 4 phase that you want to have. But then very soon after, only 10 degrees below, you have crystallization of other solids, one of them being bismuth telluride itself, and another one being another heterostructure in this family that I will talk about a bit later. So that means that if you are a materials researcher who wants to grow a crystal of this phase of a sizable size, you can only cool down the melts in this very small region between the crystallization peaks, which also entails very precise control of the synthetic temperature. And may I tell you, so in modern tube furnaces, there are very often fluctuations up to 10 degrees, despite the very good control of thermocouples. Therefore, you need a whole array of these thermocouples next to your ampule to ensure that you don't cross this borderline. So if you plate your cards right and you cool down your melt correctly, you may get nice crystals of these heterostructures indeed ordered. So you will have a bulk periodic compound with a site for with a defined crystallographic sites for bismuth and manganese. And in this system, you can also get access to further representatives of the family. So natural heterostructures where septupole layers periodically alternate with the quantupole layers of bismuth telluride. It gets progressively difficult to obtain these compounds because the melting points of these further analogs get closer and closer to the melting point of bismuth telluride. Therefore, when you get into the area of 1,610 and 1,813 compositions with 2 or 3 quantupole layers between the septupole ones, you're basically fighting against small fluctuations of temperature kinetics. And despite all the tricks, you may end up with a different compounds that you would like to. That naturally leads to some variety in the reported results on these phases, but there is even more complications that are connected to the structure of these materials. So when we looked at the obtained crystals of 1 to 4 phase by single crystal X-ray diffraction, we noticed that there is always intermixing disorder, anti-site disorder in this phase. So this position is not purely manganese and this position is not purely bismuth, but it has some intermixing with the other cation. So you have some bismuth on the manganese place in the central position and some manganese on the bismuth place in the outer position of the septupole layer. Surprisingly, when we tried to synthesize further crystals of this type by varying the conditions, we would always end up with more or less the same intermixing pattern for 1 to 4 with bismuth. So it can be argued that it is somehow kinetics controlled. We are limited, of course, by this very narrow temperature range where we synthesize the crystals, but it could also have some underlying electronic or structural effects that we are not aware of. Despite all the efforts, we could not find any additional superstructure ordering, so this disorder is truly statistical. Furthermore, in all the compounds of this type that we obtained with bismuth telluride layers in between, some degree of disorder was also present. So here you can see some ratios that we obtained for our phases from the X-ray diffractometry. there were also reports by other groups, so from the neutron powder data as well as from STM, that 1,2,4 phase is indeed slightly disordered. Back then, when it came to 1,2,4 compounds, this was not considered as detrimental, so it was close enough to the idealized composition, and the theoretical predictions on the idealized composition would also hold true for what was observed in magnetometry and partially in surface spectroscopy. So this disorder was considered a little bit like as an annoying factor, but not something that actually drives the properties of the material. One can see it also on the consistency of the magnetic properties of 1,2,4 phase that was reported to be a three-dimensional antiferromagnetic compound. So you have here out of plane ferromagnetic coupling between the manganese 2+ sides in each septopole layer, and then they order antiferromagnetically in the interlayer direction. So this data, as I said, was obtained also by many other groups, and the role of these additional interstitials, manganese in the bismuth position, was back then not that obvious. Some problems started when we moved and other groups moved to the characterization of magnetic properties of higher analogs, 1,4,7, 1,6,10, 1,8,13 phases. So there it was noticed that the antiferromagnetic transition that sets off at a lower temperature, so naturally you dilute the stacking with the non-magnetic spacers, and the interlayer exchange coupling reduces, so the transition shifts from 24 to about 13K. So this onset of an antiferromagnetic transition is very quickly followed by something that looks like a metamagnetic transition into a ferromagnetic-like, so not the hysteresis here phase. Interestingly, in 1,6,10 compound, there was not even a visible kink corresponding to the antiferromagnetic transition. We almost immediately saw something that looks like a ferromagnet. So in this paper, our collaborators developed a very nice explanation for this fact. So they said that in fact, this metamagnetic transition, so this antiferro versus ferromagnetic ordering, is in fact an interplay between the exchange coupling that is being subsequently reduced as we dilute the phase with more bismuth telluride, and the uniaxial anisotropy. But also in the series of our MBT samples, so here we have the whole family from 1,2,4 to 1,8,13, that seem to be very nicely followed. So you can see that the phases are getting more ferromagnetic-like as one moves towards 1,8,13. However, when we looked at the data reported by the other groups, we started to notice a lot of inconsistencies in this elucidation. So many other groups, so I only chose two examples here because there was also a characterization of the composition and structure. So many other groups observed that in fact 1,6,10 phase is looking like an antiferromagnet, yeah, more or less. And even in 1,8,13, you can still observe in some other reports a small onset of the antiferromagnetic transition. So what that could be, one of the ideas that now is starting to become more prominent is that these phases may have different distribution of manganese over over two cationic sites. Here, allegedly, two things will play a very important role. So first of all, the overall composition. So you may have some substoichiometric phases, you may have some voids in the cationic sites, or also the ratio between the manganese and the bismuth in each position. because it may promote a different type of coupling between the central position and the outer position. So far, there is no consistent theory that would describe all the possible cases, just because it is also very variable. But those of you who are used to this notation may notice that I here show the example of 1,6,10 compound, that the results are also quite different with respect to the overall composition and the distribution of manganese between the voids. So we have consistently under substoichiometric samples, while other groups may get a little bit closer to 1 or even lower in the manganese content. So we are now looking a little bit more carefully into the manganese bismuth telluride family, trying to find out what are the connections between the population of the crystallographic sites and the magnetometry. This is notoriously difficult because, first of all, you have very small values of these additional concentrations, and second, it's difficult to obtain these crystals. Meanwhile, there are new studies emerging. So it was also recently discovered that an antimony analog of MBT can exist. And I will be moving to that phase in a second, showing you that there the disorder phenomenon gets even stronger, and it becomes possible to somehow study it not under a looking glass, but let's say at face value, which is already being done. So there are two very nice papers here from the different groups reporting on what can happen in the MST analog. So let me go there and start by presenting the data that we got in our group. So we tried to grow these analogs by slow cooling of the melts. We quickly saw, just like other groups, that this compound does not have a narrow range of stability. It exists in quite a large interval, so it can be obtained in different temperatures. But then when you get your crystal or your powder at a certain temperature, it may have slightly different composition, and therefore different magnetic properties. So here I'm talking about crystals obtained at 610 degrees centigrade, and as you can see, this is also substoichiometric, so manganese is below 1, and we have intermixing. Those of you who could mesmerize the percentages in a manganese bismuth telluride would notice that here in the outer position, we have 3 times more manganese. And here we have a ratio between antimony and manganese closer to 1 to 1, while in the bismuth phase, it was more like 1 to 3 or 1 to 4. So we have much stronger intermixing. Well, what are the consequences of that? The consequences of that is a much larger variety of what is observed for the magnetic properties. So as I said, here in bismuth, everybody reached consent. It's an antiferromagnet. Here with MST, there is everything possible. So there are now reports that tell you it is antiferromagnetic. There are reports with ferri or ferromagnetic ordering in this phase with very different critical temperatures. And our own data, dependent on how do we obtain our powders or crystals, also shows that we are dealing with a ferro or ferrimagnet with a very varying temperature of the magnetic transition. So let me show the results we get on the single crystals with the highest TC. So this is at about 44, 45 Kelvin dependent on the sample. So here we have very strong out of plane anisotropy. So it's again an easy access ferromagnet. It is not yet clear whether the coupling between these two sides within the septopole layer is antiferromagnetic or ferromagnetic. The total saturated magnetic moment is still quite low than would be expected for the full manganese 2+ configuration. And interestingly, if we get our samples in a slightly different way, the overall magnetic scheme looks the same, but the temperature keeps on shifting towards lower values. So by now we have certain statistics on the samples. It's very interesting now to compare them between themselves as well as with the reports of other groups. So don't be afraid that I'm showing a very full table of numbers. Just like you, we are also still trying to make sense out of it. But there are already some traits here that can be named and that also are observed in principle by other groups. So let me walk you through it. If we look at samples that are obtained at the same temperature, but are annealed with a different with different duration, we observe increasing disorder. So if we first had more manganese in the central position and less manganese in the outer one, if the sample is annealed longer, it starts to become different. Nevertheless, we always observe slight substoichiometry of the samples. Even if we produce them at higher temperatures, there is still quite noticeable substoichiometry of manganese. And all these temperatures tend to cluster at around 27 or 30 K. One could maybe argue that with increasing temperature, we have slightly more manganese, we have slightly less manganese on the outer position, but so it could be a counter-propagating trend. However, it seems to not agree well with what was reported by the Oak Ridge group, where they observe by their synthetic methods different from us that the overall manganese content in both positions is increasing with the synthetic temperature. Interesting in that respect is the observation done in this archive paper by the Rada group and Chulkov group. So there they studied MBE grown thin films and they saw overstoichiometric manganese composition. The calculations there predicted that when we are having only the exchange of manganese and antimony between the positions, so the overall composition stays the same, the ordering temperature should be at about 20 K. It does not really vary too much with the disorder, but as soon as one adds about 5% of manganese excess, so we are going over stoichiometric, there should be a drastic increase in TC. Wow, seems like it is also hold true for our bulk samples. So the ones with the highest TC that we observe also maybe are over stoichiometric in manganese content. So while it will take quite some time to study this metrics, to make some sense out of it, it would be very interesting to see more calculations done on the disordered models that of course very quickly becomes a very large superstructure if you really want to look at the disorders of 5 to 10%. So here I'm not showing any details from my group in cooperation with theoreticians or other groups of theoreticians working on these disordered models. This is still quite ongoing, but I want to show you that in fact this family already with the idealized compositions was found to be very flexible. So if 1 to 4 should be an antiferromagnetic topological insulators already, or insulator, already for 1 for 7, different possibilities become feasible. So the energetic difference between different magnetic ground states becomes smaller, and one could imagine a scenario in which this compound becomes ferromagnetic or antiferromagnetic, giving an antiferromagnetic Ti or a Weil semi-metal. While if the idealized composition is already prone to such flexibility, it's very well possible that the disordered models will provide an even larger playground for coupling different magnetic ground states in the topology, if we will be able to, first of all, discern the value of different factors, and second, to control the samples so well that we can deliberately produce these different stoichiometries. Well, with that, I would like to wrap up my talk and to invite you to listen to the follow-up of it given by Hendrik Bentman later in this session. He will be touching upon surface spectroscopy experiments performed on our samples. There, it was also observed that this theoretical prediction does not really hold all too well for these phases. So there are some intricate things with a gap being opened in the paramagnetic state, or some other samples different from ours being reported to have a closed gap in the ordered state. There were possible explanations for that in the literature, pertaining that there could be some disorder of the moments at the surface of the samples. I think that nowadays we can also safely say we should look more into disorder, into intermixing in the samples to maybe be and maybe be able to explain these discrepancies in spectroscopy. Here on my last slide, I summarized what is now ongoing in the MBT family. Let's say on the material side, we have very exciting prospects. So if it will be understood how to control the TCs and the magnetic order in these phases by adding different transition metals or by tuning the intermixing disorder, we will be able to push the critical temperature higher. And if we also understand how to keep the topological properties, non-trivial topology of the electronic band structure of these phases simultaneously with rising the TC, we will have even better candidates for quantum anomalous Hall effect. Thank you very much for your kind attention. And with that, I finish my talk and am open for questions. Thank you.
Thank you, Anna, very much for this very nice and clear talk. And I see there is a question from Thanasis.
Yes.
Yes, unmute
Yes,
yourself and ask, please.
Okay, thank you very much. Thank you for this interesting talk. And I wanted to ask, in one of the other phases, for example, the 147 phase, it could be that the quintuples with the septuples do not alternate sequentially, but you may have two quintuples followed by two septuples, so it could be a mixing of the layers, let's say, not
sure.
So that does it play any role in the magnetic properties, and can you control that with your growth technique?
Thank you very much for this very on point question. Indeed, control of this layer sequence becomes increasingly difficult. So to your last question, if we can control that and if we know that, I can tell you that we know that on certain length scales. So we always study the samples by X-ray diffraction, showing us the periodicity of the crystal lattice. So let's say for small single crystals on the scale of hundreds of microns, we know that there is very little disorder, or let's say macroscopically this crystal is still a very well ordered lattice. So even if there are some defects, some occasional skipping of the layers and so on, they're very low in number. So of course, when we move to larger samples, like, I don't know, ones that are about 1 millimeter in lateral dimension, this is not a single crystal anymore. This is more like a twin consisting of different crystals. We tried, however, to also study these large pieces by diffraction. So in this case, it would be X-ray powder diffraction. And it also shows us that mostly these larger samples are also they also belong to the same lattice, meaning that to the large extent they're still ordered periodically. And as for the variation of the magnetic properties, so yes, it exists to some extent. We try to do it deliberately, so to produce samples that are mixtures of two phases. And it was possible to see slight variation of the TC for one phase, and then already a superposition of two different transitions indicating that we have two different phases. So at least there is no smooth transition in the critical temperature and the general way how magnetization curve looks between the phases.
Yeah, so if you disturb the order, the perfect order, then do you expect a higher TC or a lower TC?
There are very many ways to disturb the order, and then there is also, in my opinion, some critical mass of disorder. Yeah, so if we, I did not study aperiodic stackings, so that are closer to the maybe these heterostructures that I showed on the introductory slides, where you really have statistics. So we don't have such crystals, we don't study them. But I think that mostly for the, so if we look at the energy scales of these exchange couplings between the layers, so already for 147, when you have one spacer, the interlayer coupling, magnetic exchange coupling, becomes much lower than the in-plane one. And I think that this local disorder, so the one with intermixing, is much more affecting the magnetic couplings and the order than the ones over the layer.
Okay, thank you very much. Thank you.
Thank you.
Are there more questions?
Yeah, I
Okay.
have a question. Thank you very much for the talk. It was super nice. All the data there. I saw that there is, in principle, there should be in the saturation point, the magnetization, the value of manganese should be around 4 or 5 magneton war. But then I saw many articles when they obtain like 2, you show something like 3 point something. And I wonder if you know which one is the reason why people cannot get the 4 or 5 value that is predicted for 5.5.
So yes, indeed, this is a general trend for this type of materials. So there is one article where I think, so it was a high field measurement. I want to say it about 10 Tesla, but could be 12 or 14, where the saturation has been reached. So the reason for that, as my colleagues in magnetometry pertain, is in very strong anisotropy of these phases. So basically, when you perform the field measurement, you have slightly non-collinear configurations, and it saturates very slowly. So you only have a part of the magnetic moment saturating at lower fields, and the rest happens only at the higher ones.
Okay. Thank you very much.
And there is a question on the chat, and it says, "Hi Anna, nice talk. You also mentioned the MBE growth. Are there also similar disorder for the MBE grown crystals? Thanks."
Sorry, are there? Could you repeat?
Also is there also similar disorder for the MBE grown crystals?
Thank you very much. So as far as I understand the present state of the literature, there is no considerable notable disorder reported for manganese bismuth telluride films. So I'm aware only of 1 to 4 grown periodically as a thin film with 147. There are problems, and well, if there is disorder, it's minuscule, it's not really being discussed. But in this archive preprint that I showed, that I flashed by on the last slides, that is about MST film, manganese antimony telluride film. Yes, there is disorder. So it was deliberately looked at. It's about 5 to 10 atomic percent in each position. And this is also over stoichiometric samples, so they have excess of manganese. And that apparently very much changes the properties. So they also report a very high TC of about 45 to 50K.
Okay, thank you. Are there more questions? Okay, I have one myself. Among all the materials that you have run, which one would you consider to be the best candidate for a antiferromagnetic topological material?
I'm very much interested now in this manganese antimony telluride samples because the temperature is so high. However, I think we really need to get very consistent spectroscopy data. These are p-doped samples, so it's very difficult to assess whether there is magnetic gap. And if I can answer your question such, I think the most interesting samples would be manganese antimony bismuth tellurides, so quaternary systems, where one would control both the doping on the bismuth side to get a nicely compensated semiconductor and to get enough disorder on the manganese side to have a high TC. Whether it is achievable, that's another question.
Okay. And one last question. Have been there any attempts to like substitute the magnetic atom? Because okay, you change bismuth with antimony, but what about manganese? You cannot substitute it with another magnetic atom?
There is a very nice theoretical paper, once again, from the Chukov group.
Yeah, but I mean experimentally.
Experimentally, it is being tried. So I would say that we are trying it as well. We are aware of some other groups trying that, but it seems not to be very straightforward. So if you just replace manganese, let's say by iron and so on, it does not proceed that easily. It's possible that it is connected to these very specific synthetic conditions that are required, and one just has to search for them. And hopefully one or the other group will get lucky and obtain. So
okay, so experimentally, you only tried iron.
We tried different transition metals and we are still trying.
Okay. Okay, thank you. Are there more questions? Okay, now let's thank the speaker again and let's swap to the next talk.
Yeah, thank you very much for your attention.
Thank you, Anna.
Hello.
Okay, so we move on to our next speaker. Let me introduce you to Jagadesh Modera from the Massachusetts Institute of Technology. He's a leading expert in magnetism, superconductivity, and spintronics. And today he's going to talk about topological superconductivity and Majorana pair in gold. So, Professor Modera, whenever you want.
Yes, can you hear me?
Yes, we can hear you.
Oh, very good morning or good afternoon, depends where you are. So first of all, I want to thank Sergio for the invitation. Secondly, it's a pleasure to be talking about our work in this workshop. So as she pointed out, the topic is topological superconductivity and the search for Majorana in gold. This program is funded by John Templeton Foundation. One second. Yeah, John Templeton Foundation, then also Office of Naval Research and National Science Foundation. So we started this work several years ago when the theoretical work by Patrick Lee and Andrew Potter was brought to our attention. They approached us to see if you can search for the Majorana in the superconducting surface state of the gold. So that was the starting point about 10 years ago now. Andrew Potter was a PhD student with Patrick Lee at the time. They had a couple of papers published by then. One was about the superconductivity in the surface state of gold. Other one is how we can go about looking for the Majorana pair. So we formed a team with a very close collaboration with Patrick Lee. He's MIT. And then my postdoc at that time starting was Pang Wei, who is now a faculty in Riverside. Then later on, Sujit Manna joined, and he is now a faculty in IIT Delhi. So theory collaboration with the Patrick Lee is by also Katie Law and YG from Hong Kong Science, University of Science and Technology. So current postdocs are Yasin Hu and Alessandro Gorisani. They're working on that. Okay, the outline of my talk is about how to get the gold epitaxy 111. That's what we need, and at the same time keep the surface state intact. We have to grow this epitaxial layer on some superconducting platform to drive the system into superconducting state. So then search for the surface state superconductivity in gold 111. Then of course comes the tuning of the Fermi level, and then look for the Majorana pair. Then how can you go from here to the next step, which is a major step, creating topological qubits? Okay, it was known very well that all the way back in the mid-90s that the surface state of gold 111 is a very large Rashba spin-orbit splitting. It's on the order of 110 milli-electron volt. So that's an excellent platform looking for Majorana. So our goal was to drive the surface state into superconducting state. Now, what Patrick Lee and Potter said was that if you can couple the gold to another superconductor, it could be S-wave superconductor, then the surface state, although it is not really in touch with the bulk band of the gold, it can still acquire superconductivity by the inelastic scattering of disordered defects, and also inelastic scattering by excitations such as phonons or pair tunneling across the two bands. So this is an indirect way of actually inducing superconductivity, whereas the bulk gold can be typical conventional way of proximity coupled superconductivity. Once you have this gold surface state in superconducting, then you can look for the Majorana. That was their prediction. So, and the next thing, of course, they said was once you have superconductivity in the surface state, then you actually look for this Majorana. For example, the theory pointed out that if you have a very large wide sample, then the Majorana wave function can be found all around, but you start narrowing it down, then you can actually, when the width is on the order of the coherence length, then the Majorana, this state actually gets localized in two ends. So that is the criteria. So what we need is, first of all, of course, superconductivity in surface state, and you have to have a very large magnetic field. And of course, we know that surface state of the gold 111 is very large spin orbit splitting. So this is an ideal system. So that's what we were after. So in order to do this, one of the ideal way would be to use a scanning tunneling microscope to look for this and localized Majorana state. Okay, so Kitaeva's prediction way back about 20 years ago was that if you have under special conditions, a fermion state in a superconductor can actually split non-locally into two parts. This separated in space. The distance is not really important because it can go any length depending on the dimension of the wire, and then you can actually see the Majorana pair. Our goal was to see the Majorana pair appearing together. That was part of the goal, because that is where the interest is in trying to take it towards the robust Majorana topological qubit. So that was our goal. So we know that there has been a lot of work in the Majorana field, as you see here, a whole lot of them. And then one of the very advanced ones is using semiconductor, as you can see here, indium antimonide, indium arsenide, and so on and so forth. And this was actually the way back prediction by Fu and Kane was that it should be one-dimensional p-wave superconductor, then large spin orbit and magnetic field, and so on and so forth. Then other platform is having a atomic chain using STM, then you can actually look for the Majorana as well. The third one is, of course, looking for the flux lattice in a special superconductor, then you can see the Majorana forming at the ends of the flux. So our goal was to actually search for a readily scalable and tunable system, which has also a robust possibility of creating the Majorana, which means it is supposed to have a very large spin orbit. compared to the one on 110 millielectron volt in the gold, these semiconductor platforms have on the order of tens of microelectron volt. So this is about 1,000 times bigger, as you see. Right away, we start with a very interesting system. Now, next goal was to establish the Majorana zero mode and find the two pairs simultaneously appearing. That's what we want to do. So what Patrick's theory said that if you have this very large surface state, I mean, Joshua splitting in the system, then we can actually, if you can tune the Fermi level, I mean, rather band bottom all the way towards the chemical potential or the Fermi level, then you can actually create this very few states in the system instead of having many modes, which will be diluting the Majorana wave function. So if you can narrow it down to just a few, then you can actually see this pair formation at the end of the wire. The problem is this Fermi energy is about half the electron volt from the band bottom. So it's a gold system. It's a highly conducting system. So how do you actually bring it up? The second thing, of course, we need to have a very large magnetic field. We are talking about the STM. The field has to be in plane. So normally people have field out of plane. It can be very large, whereas in plane field, very few systems exist. In our case, we have a 5 Tesla parallel field STM setup. So we found that both the problems can be solved by having European sulfide as a top layer in the system. So first of all, we create the superconductivity in the gold surface state, then apply a large magnetic field. In fact, part of the field is provided by the European sulfide exchange, and that creates this topological superconductivity in the gold, and then actually that can lead to Majorana pair. So the second thing, of course, this large exchange field is not the only thing the European sulfide does. It also actually tunes the Fermi energy. In other words, it actually moves the band way up in energy scale. So it actually brings to the right condition where we want to see the Majorana. So that we had actually advantage both ways having European sulfide on top of this gold surface state. Another important thing is this European sulfide did not destroy the surface state of the gold. So we grew this gold on the vanadium. Vanadium is a superconductor of about 5 Kelvin Tc. And if you have a very thin gold, such as 4 nanometers, then actually you can induce superconductivity very easily in the gold. And then the surface state, of course, gets expected to become superconducting by the indirect means. So the quality of the film is very good. We have a very nice flat film, and also coupling between the gold and the vanadium is very good because it's all done in an ultra high vacuum system. So we can see from the STM measurement, the surface is very flat and very clean. As you can see, the atomic arrangement of the vanadium 110, and on top of that, the gold that is grown is 111. So it's also nicely well ordered and grows really well. So it is a flat system. So in fact, gold starts forming continuously by about less than a monolayer. Now the second thing, of course, we had to do is, okay, we found the epitaxy of gold, very high quality. Next is, of course, surface superconductivity. To do that, first thing what we did was we created a planar junction, sandwich junction, typical. So as you can see, the stack structure, on a sapphire, you grow the vanadium and the gold. Then you put the tunnel barrier European sulfide. The aluminum, which is a superconductor below about 2 Kelvin, as a top electrode. So when you have stacks such as this, and it's a large area, 150 by 150 micrometers, you cool down around 4 Kelvin, you already see some sign of the gap opening up. So then as you cool down further, and you can see the current peak forming nicely. Below about 3 Kelvin, or rather close to 2 Kelvin, you find that the single peak actually split into 2 peaks. These 2 peaks actually show that there is something happening in addition to the standard superconductivity of the gold. So that's where we are sensing, right? So this second peak we can clearly see is due to the surface becoming actually superconducting, surface of the gold. In other words, the surface state of the gold shows superconducting behavior. Now, as you can see, the conductance measured at 1 Kelvin, where the aluminum is also superconducting, then you can see a very nice sharp features of these 4 peaks on each side, and this can be nicely attributed to the surface gap of the gold and also the bulk gap of the gold. Aluminum, of course, is a typical BCS superconductor, and you can attribute all these peaks very nicely through 3 gaps. One gap is, of course, due to the vanadium. The other one is due to the gold. Vanadium gap we know, and the gold is 0.61, and whereas the surface gap comes out to be around 0.4 millielectron volt. So we do have a very large superconducting gap that forms on the surface of the gold. So this fitting is done by SIS tunneling, and in fact, it can be only done by two gaps in one of the superconductor, which is the bottom electrode. Now, as I mentioned before, this superconductivity of the surface of the gold is due to the indirect exchange of the particles or the pairs across the two bands, because the surface band is isolated from the bulk band. So this is unconventional, whereas the vanadium bulk of the gold is actually becomes superconducting by the conventional proximity effect. So anyway, what I wanted to point out is the surface state has a gap of around 0.4 milli-electron volt. Okay, now we have a superconductive surface state of the gold. Next thing is look for the Majorana. Of course, we can use the scanning tunneling microscope to look for this Majorana, because we are able to scan the area, completely area. So that way we can actually look for the complete spectroscopic feature of all around the nanowire, for example. So now again, this is the STM study of the vanadium 1110, and also you can see that they can clearly see on the gold, which is grown on that 111, surface state is intact, and you can see around 0.5 electron volt. Now, if you cool down to very low temperature, we can actually see the vanadium superconductivity nicely forms with a very hard gap, you can see, and about 0.83 milli-electron volt. On top of the gold, when you actually scan, what we find is we still have the surface state, as I mentioned just now. And in addition to that, you can see superconducting gold surface as around 0.36 Kelvin. You see a nice hard gap, and it's a little bit broad because our tunneling microscope uses a very large modulation signal in order to get a good amount of signal. So the interesting thing is this is all after forming a nanowire of the gold. That means even after forming nanowire of gold of any kind of dimension, for example, our aspect ratio is around 100 nanometers versus several microns long. So despite of all these patterning issues, you still have the surface state intact. And second thing, you can see the very sharp edge of the gold nanowire. So these are all very interesting. And then in other words, we can have a very good control on actually patterning this gold for the future, for creating network. So next thing is, of course, so how do you bring the chemical potential down, rather than bring the band up, surface band bottom up? So we introduce europium sulfide. In other words, we deposit a submonolar layer of europium sulfide. It forms islands in the gold. This is the gold nanowire. You can see the islands. One of them you can see here. And you actually scan spectroscopically scan the surface. On the gold, you can see, as mentioned before, around 0.5 electron volt. That's where the Fermi energy, that is band bottom from the Fermi energy. Whereas on top of the europium sulfide, it has shifted all the way to around 200 milli-electron volt. In other words, even with such thin layer of europium sulfide on that, you can see the chemical potential as lowered. So this bottom has gone up. Now, as I mentioned, europium sulfide affects in two different and important ways. One is it modifies the surface potential, which gives rise to the shift of the band. And the second thing, it provides a large exchange field. So here I can tell you how the exchange field is affecting. For example, if you have europium sulfide adjacent to a metallic system or some conducting system, these charge carriers in the system, in our case is gold, is subjected to very large exchange field by the europium ions. Europium ions 2+ have a very large magnetic moment. It creates a very large exchange field. These fields can be as much as tens to hundreds of Tesla. So in other words, at the interface, you have a very large exchange field present. So in addition to that, of course, this alignment of the system is very, very easy. So it's also very intact. You can have a very nice ferromagnetic layer, even down to one nanometer. You can see a nice hysteresis loop. So it's a very ideal system to actually create an interfacial exchange field. So that has benefited us tremendously. For example, as you see here, we have now introduced 2 monolayers of europium sulfide on the nanowire. That means you have a thicker layer now. Now the band moves way up, very close to the Fermi level. In other words, it comes within about 20 to 30 milli-electron volt. This is where we want. That means we have only very few modes to deal with, which means we have the probability of seeing Majorana much higher. So for example, take one of these islands. This is the europium sulfide island on the surface of the gold. Then you can actually cool down to 360 millikelvin, and actually scan all around the surface, around the edge of this island, what you find is very nice superconducting gap. In other words, we actually tunneling into the gold surface very close to the island. We are not able to really scan on the island because the island is around 2 monoliths, so the signal is very, very small. So it becomes rather hard to get a very good quality signal on the surface. So we have to go very close to the edge. So all around 1 to 8, you see a nice gap. Now apply a magnetic field around close to 5 Tesla, that's the limit of our system. We clearly see the gap is still maintained in 7 in this region. The field is along this direction. The around 7, 8, and also 5, 4, you can see a nice gap still maintained, as you can see here. So there's 2 of them, 4, 5, and 7, 8. You can see a nice hard gap. Whereas when you look at the spectrum close to this region and also just the opposite region, you see the zero bias peak showing up. So if you see clearly that this peak appears at the opposite ends of the island, and that also has a threshold field on the order of about 3.5 Tesla. So, and in order to show you even a better signal, what we have is another island which actually strides very close to the edge of the gold wire. This edge of the gold wire is here, and this island happens to be on the edge of the gold wire, one end. So if you again scan for all the way around this one, spectroscopically see that you have complete gap opening up all the way in zero magnetic field. I see nicely. These are all shifted for clarity. All of them have a hard gap, very nicely defined superconductivity. Now, if you apply a magnetic field along this direction, then what you see is between 2 to 7, you still have nice hard gap, as you can see here, even at about 5 Tesla. There's a little bit of filling because of the large magnetic field, and it could be superconductor a little bit. Whereas what you find is at position 1 and 8, you have a very strong zero bias peak appearing, as you can see here. So in order to show you that these peaks appear at the threshold field, which is not very far from each other, see the next plot wherein we have in zero magnetic field, nice hard gap here. As you start increasing the field, you see the gap still continues to be there. And by about 3.5 to 4 Tesla, both in position 1 and position 8, you see the zero bias peak opening up. And by about 4.5 Tesla, you see it's very well defined. And that becomes even better by 4.8 Tesla. Unfortunately, our field is only about 5 Tesla, so we couldn't go any further than that. You can see how sensitive it is to the magnetic field. So you clearly see that they have a threshold field to appear the zero bias peak, whereas all other positions here, anywhere here, you see nice hard gap. Now, if you look at the two-dimensional plot as a function of field, what you find is, of course, in the beginning you have this is the large conductance here, whereas here the gap opens. Gap is the superconducting gap. As you increase the field by around 3.5 Tesla to 4 Tesla, you see very this is the transition region, which is not very sharp, which is a little bit broad. That can explain why a little bit variation in the appearance of the zero bias peak between the position 1 and position 8. So you can clear as a function of field nicely the peak appearing as a function. So this again because of the weightage factor. In other words, the zero bias peak is determined by the tunneling factor, which is gamma by gamma plus gamma p, where gamma p is a quasi-particle Poisson rate, which is very high when you're at near the threshold. That means the gap, topological gap is very small now. So as you increase the field, you can go away from this, the gap actually increases. As a result of that, you have less of quasi-particle poisoning, then you can see the Majorana peak appearing a lot more well-defined. So there can be slight variation in position 1 and 8 that can actually also explain why you have a little bit variation. So now to show that this peak appears only at this point and not anywhere else, anywhere even in this direction, we can actually, once you find the zero bias peak here, which we call as a Majorana pair, then you go away from it, and you go away from it by about 10 nanometers or so, you see the peak disappears. This is very close to the edge, is the first curve, and then as you go away from it, you see the nice hard gap opening up. One thing I wanted to point out is the zero bias appears, Majorana appears right underneath this edge. So, but since we are not able to tunnel at that point, what we are looking is we're actually sensing the tail of the Majorana. That's what we see at this point. We are very close to the edge, which is on the order of like 1 or 2 nanometers from the edge. Then you go away from it, you can see it's leaking down. That's the same thing happens in other case. So this kind of signature we have seen at least in 20 different islands, and complete measurements are done on about 6 islands. So that way it's not one of those one type thing. It is actually repeatable in some sense. So now if you look at the theoretical simulation based on our experiment, in other words, it's exactly simulating what we have. If you have an island actually at the edge of the nanowire, then you find that the Majorana wave function is a lot more concentrated at these 2 points compared to having an island which is in the middle of the nanowire. As you can see, in the middle of the nanowire, what happens, the edge of the this island, you can see the slight distribution of the Majorana wave function. That means it's not very strongly concentrated at one point. Whereas when you have this kind of some sort of singularity, you can see the Majorana peak more concentrated. That is what we see in the experiment. So these peaks are not as well defined compared to the 1 and 8. So if you look at this, this is the gap I was talking about. These are the Majorana pair peaks, and this is the topological gap here. So this topological gap depends on the actually bulk superconducting gap of the gold. So in order to actually increase this topological gap, that's what we want, so that you can have a cleaner Majorana signal, then you have to increase this gap. So since we use vanadium, which is a TC around 5 Kelvin, that is limited by that. Now we are able to actually see a bigger gap superconductor working as well, but we are still halfway there. We're not finished that yet. For example, we have done with niobium and also niobium titanium, and we also work with niobium nitride. These are all superconductors with almost twice and 3 times the TC of the vanadium, which means the gap is also very large. So we should be able to see a much more robust Majorana forming and more well-defined. And second thing, as I mentioned earlier, is that the modulation signal we used was very large. So according to our modulation signal, our actual measurement is more close to this kind of feature compared to what we expect to see at 350 millikelvin. So we have broadening due to the modulation and also the noise in the system. So our STM is not located in a very ideal place. So given that one, we are not able to optimize this yet. So that's what we are actually working right now, how to improve the signal with a better electronics and also a better superconductor with a bigger energy gap. So to summarize this one, what we have shown is in the case of gold surface state, we can induce superconductivity. It's an unconventional superconducting state. So in addition to that, on the gold surface, rather we actually have a longer wire of that, one expect to see the Majorana, whereas we were able to see the Majorana using European sulfide. In other words, we don't need to really actually make the island, nanowire of the gold. We can actually have a platform of gold. You can have the island in the middle. You can have actually the surface, your Majorana can be defined at any point you want. It means it's nicely patternable anywhere you want. So this is one of the very versatile and scalable system one can expect. And the second thing is, since it has a very large spin-orbit energy, it's a very robust system for creating Majorana. So there is simplicity of architectural growth of the system. Nanofabrication is straightforward. It's a metallic system, and also large spin-orbit means it's a very good platform to look for the next step, take the next step rather to create a Majorana qubit architecture. So we are actually doing this one right now. We have a program with the National Science Foundation, wherein actually we can actually, our goal is to go towards topological qubits. For example, right now, what is available in the, for example, the quantum computers state of the art, even 53 qubit has a very complex operating system. As you can see here, the wiring is very, very complex. So despite that, it has a very large error correction, and also its scaling up is very, very hard. That has taken decades to reach this level. So how can one build a better qubit which is less prone to these errors? Kitaway proposed way back about 20 years ago that one can have fault-tolerant quantum computing using Majorana zero mode. That's our goal. For example, if you look at the superconducting qubit, it is actually sensitive to all kinds of noise. Every possible noise can actually affect that. Secondly, you need to have about 1,000 qubits to form one good logical qubit. So it is actually very intense, both resource-wise and also scaling up is very, very hard. So our goal is to go towards this topological qubit. For example, one of the very ideal thing about the Majorana is that we can store the information in a highly non-local way. So which means it is not perturbed very easily. It is immune to the local disorder or perturbance. So which we expect to have a large coherence time in this system. And also it's physically protected and error resistant. So there are two states one can expect in this. One is either electron occupied or unoccupied. That defines the parity of the system. This can be measured actually using just a simple circuit such as shown here. This is the model by Liang Fo and his students, the theoretical model, where they predicted that you can have an interferometric circuit such as this, where one arm is actually the topological superconductor with the Majorana present, and the other arm is actually just as the junction, the conventional superconductor. You can measure either the flux change or the current change in the system. Depending on the parity, you can actually detect the state of the parity state of the system. So that tells you the quantum state of the system. So once you are successful in that one, then scaling up into this structure or even this structure, then you can actually create a qubit. And the path of the current or path of this conductance can be defined by the either side gate or the bottom gate. You can have a different path. So that allows you to determine all three Pauli operators X, Y, and Z. So that should be able to take you to the next level. So this is what we are doing. Of course, this is very challenging, but we are starting out with a very stable and very robust platform. At least we have a very good platform to start searching for this qubit. So with this, I want to thank you very much for your attention.
Thank you very much for this super nice talk, and the last explanations were awesome. Okay, so there are a few questions and I'm gonna read them. Dear Professor Modera, thanks for the nice talk on STM measurements. I have a couple of questions. I wonder if the transition of gold 111 is general phenomena provided you choose a thin sample?
Yes, on the same sample.
Okay, that's the answer.
The planar junction was done on a different sample, whereas the STM was done on a entirely second different one.
Okay, another question. Thanks for the nice talk. Could you measure simultaneously the appearance of Majoranas at both ends of the islands?
Well, it's an STM, right? We have to measure one first and the other one. So after you scan one end, then you go to the other end and then you measure. As you change the field, you again do the same thing. So as a function of field, you scan first one end and then the other end. So we cannot actually measure both ends simultaneously. So one after the other we measure.
Okay. Dear Professor Modera, thanks for a nice talk on STM measurements. I have a couple of questions. Sorry. Okay, and a question just disappeared. Thanks for the nice talk. I wonder what defines the position of the zero bias modes in the rounded shapes European sulfide island. Why don't you observe a zero bias mode all around the island?
Because that's where the Majorana forms, opposite ends of the island. This is what they expected. In other words, it actually focuses, or rather concentrates on two ends of the island, because this acts as a one which actually creates the right position for the Fermi energy, and also you have the enough magnetic field there. So it is very conducive for observing the Majorana pair. So all around you don't see, because the Majorana wave function is not there all around. It's only in the two ends of the island.
Okay. How flux quantums are measured?
Oh, this is a program we just started. One of the way we are thinking about flip chip geometry. I mean, there is a lot of progress in the superconducting qubit, right? So one of our team members is an expert in this one, Bill Oliver. So they have years of experience in actually creating flip chip geometry. So you can measure the flux using the squid.
All right.
That's what we expect to do. We are not there yet.
Dear Prof. Modera, thanks for a nice talk on STM measurements. I have a couple of questions. I wonder if the transition of gold 111 as a superconductor is a general phenomenon provided you choose a thin sample?
Yeah, gold actually shows superconductor rather easily. In fact, we have, as I mentioned to you, we have been working recently on other superconductor coupled to the gold. They all show very nice energy gap. In fact, we are able to actually double the surface energy gap already.
Can you explain a little bit detail about how the surface state converts itself into a superconducting state? Would be nice if you can suggest some computational work done on this.
Right. You saw the very early stage. You should look at the research theoretical papers by Patrick Lee and Andrew Potter way back, I think 2010, 2012, that time period. So they have explained there are several mechanisms. It's not details not known, but several indirect ways of actually scattering across the bands. So it's an indirect scattering of these particles, either single fermions or it could be pair of electrons. They scatter across the bands and pick up superconductivity that way.
Okay. Are there more questions? Okay, in all talk, your superconductors based on conventional superconductors. So what happens if we study by unconventional superconducting concept?
Such as what, for example?
Such as what?
Oh, in fact, as I mentioned, the niobium nitride, niobium, niobium titanium, all of them are able to drive the gold even surface into superconducting state. We have not extensively studied other unconventional ones yet, such as high TC superconductors. So important thing is we need to be able to get a very flat, very thin gold on the surface. So creating a unconventional superconductor with a very flat surface, very clean surface, and coupling the gold on that, it could be one of the challenges one have. So one can also do, for example, niobium diselenide. You can try that also.
Okay, another question about Majorana fermion effect. Is there any dependence on gold thickness?
Yeah, this is a very nice question actually. So the gold thickness determines the surface gap, for example. The gold layer is too thick, then the surface induced gap becomes weaker. Whereas if you make it very thin gold layer, then the surface can couple to some extent with the bottom conventional superconductor. That means the gap can be much larger. Whereas right now, what it is doing is only depending on the indirect scattering mechanism with the bulk gold. So if you're able to couple directly to the bottom, not too much coupling, but just a little coupling. If too much coupling, it could be a problem for containing the Majorana.
Okay. Okay, I think there are no more questions and we should move to the next speaker. Thank you very much again.
Thank you very much.
And Hendrik Bentman, are you around? Ah, yeah.
Yes, I am.
Okay, you can share your talk, please.
Okay, but I think first must be, oh yeah. Where is it? I don't see the option at the moment.
Oh.
Ah, no, it's there, sorry.
Okay, so our next speaker is Hendrik Bentman from the University of Würzburg, and he's gonna talk about imaging topological states in photoelectron spectroscopy from magnetic topological insulators to vile semimetals. So, Hendrik, please.
Yeah, thank you very much for the introduction and also to the organizers for the kind invitation. So in this talk, I will present recent photo emission results on two types of topological materials. And in particular, I will look at magnetic topological insulators in this manganese bismuth telluride based class of magnetic van der Waals materials, which has already been very nicely been introduced by Anna in her talk in the same session. And then later I will present recent results that we obtained for the vile semimetal tantalum arsenide, where we will basically be interested in the question to what extent we can actually address really the non-trivial topological properties of the electronic states in these materials via momentum resolved spectroscopy. Okay, before starting, let me first acknowledge my collaborators. So this is work done in Würzburg in the group of Friedel Reinhardt. And much of the work has been carried out by very skilled PhD students. So the work on the wild semi-metals was mainly carried here by Max Unzelmann and Tim Friggemeier, and work on the magnetic topological insulators was carried out by Rafael Vidal and Philip Kagerer, and also there were very important contributions by Celso Fonari, who's a postdoc in our group. And then furthermore, I'd like to highlight in particular a very nice and long-standing collaboration with Anna Isajeva, who's now in Amsterdam. And also in the context of this talk in particular, we had very nice laser ARPAS collaborations with groups in Hiroshima and also in Jülich. Okay, just as a brief introduction. So when we start with the conventional topological insulator, it was realized early on that introducing magnetism, despite breaking time reversal symmetry, is not really detrimental for the topological properties, but rather the introduction of magnetic order introduces new types of topological states. And one type is seen here, where due to magnetic order, a gap in the topological surface state is induced, but new types of one-dimensional topologically protected edge states are generated, which in real space form these chiral one-dimensional channels, which can be used for dissipationless charge currents. So compared to conventional topological insulators, the number of materials that really actually combine this interplay between topological band structure on the one hand and magnetic order on the other hand is still rather low. So there are not many materials that realize this interplay. So one important task in the field at the moment is to search and to establish and to control new types of materials where really this interplay can be robustly observed. Now, one other important property of topological insulators is that they cannot be tuned, or their band structure cannot be tuned by some external parameter into the one of a normal insulator without going through a metallic phase. This is one of the defining features of a topological insulator. And it was realized that actually these metallic phases that lie at the phase boundary between the normal and the topological insulator can also display interesting topological properties. And one example is this well-known wild semi-metal, which appears at, or actually over an extended region at this phase boundary once the inversion symmetry of the system is broken. So the breaking of inversion symmetry is important in this case because it allows spin orbit coupling to split the electronic bands already in the bulk. So we get spin polarized bands in the bulk, and then these metallic state here features band crossings between spin polarized bands, which generically constitute monopoles of Berry curvature. So at these metallic band crossings, we have monopoles of Berry curvature in momentum space, and these monopoles can be associated with a topological invariant, basically the surface integral over a sphere surrounding these wild points. And this topological invariant protects these band crossings. And similarly, as in topological insulators, the bulk boundary correspondence implies surface states which are generated from this non-trivial topology in the bulk. And these, according to theory, take the form of Fermi arcs, so non-closed Fermi surface contours, which connect the projections of the bulk wild points. And the question that I will address in particular, to what extent can we really image this non-trivial topology of the electronic states, really the Bloch wave functions in momentum space using spectroscopy. Okay, the method that we are using is angle resolved photoelectron spectroscopy. I will just give a brief introduction here. So we use light to excite photoelectrons, which are then analyzed as a function of energy and also emission angle. And via energy and momentum conservation laws, we can deduce back from the photoemission intensity distribution on the band structure in the solid, basically. So we can even go one step further, because all the topological properties that we have seen are not only associated with the dispersion of the electronic states that we can address with ARPAS, but also intimately related to the actual Bloch wave functions. And these Bloch wave functions, in fact, also enter the photoemission intensity distribution, namely as the initial state of this photoemission matrix element, which furthermore also contains the exciting light, the electric field of the exciting light, and the final state of the outgoing photoelectron. So the idea is now to use these so-called matrix element effects, so to really study the intensity distributions, for example, as a function of the polarization of the exciting light. So this would be so-called circular and linear dichroic signals, or really detecting the photoemission intensity as a function of spin, so really resolving the spin to detect the photoelectron spin polarization, and to relate these momentum distributions to the, as far as possible, to the intrinsic spin-dependent properties of the electronic structure, and eventually study the topological properties of these states. Okay, let's start with the first part on the magnetic topological insulators. So this topic was already very nicely introduced by Anna, so I will not spend too much time with the introduction. We have this layered van der Waals compound, which resembles this well-known topological insulator bismuth telluride, but now we have introduced additionally these manganese atoms in the center of the sep-tupel layers, and it turns out that these for the 1,2,4 compound, these magnetic moments order antiferromagnetically and layer-wise paramagnetically, and the DFT calculation for this situation shows this gapped topological surface state. So this 1,2,4 compound has been studied quite extensively by ARPAS already. What I will focus on in this talk are a bit more recent experiments that we performed on this 1,4,7 compound, which was also already introduced by Anna, where this magnetic sep-tupel layers are kind of sandwiched by non-magnetic bismuth telluride layers. So this is an overview of the results. First of all, here on the bottom right, we see results on the magnetic properties, where, as Anna has already mentioned, one now sees interesting deviations from the strong antiferromagnetic state observed in 1,2,4. One observes increasingly ferromagnetic-like properties. And in the ARPAS, we have now to take care of the fact that in this compound, we can have different surface terminations. So we can either have a surface that is terminated by a magnetic sep-tupel layer, or a surface that is terminated by a non-magnetic quintupel layer. So depending on which of these van der Waals gaps defines the surface. And it turns out that on both types of surfaces, we observe topological surface state, but the electronic structure looks considerably different. So this is the result for an MBT termination, where we can identify this topological surface state here, forming a Dirac-like dispersion. And this is the result for a bismuth telluride termination, where it looks a little bit more complicated. And in particular, we see here at certain energies a reduction of spectral weight, giving rise to something like a gap-like feature in the intensity distribution. So now I will look a little bit more in detail at the properties of these states and try to really confirm as far as possible that these are indeed topological states. So starting with the 1,2,4 terminated surface first, what we looked at is the circular dichroism signal. So this is shown here. So basically we measure photoemission intensity distributions for left and right circularly polarized light. And this red-blue color code is the difference between the two intensities. And what we observe here is that at this point that we previously identified at the Dirac point, we in fact see a reversal of the sign of the dichroism when comparing energies above and below the Dirac point. And this is actually an a first sign that this is in fact a helical Dirac state. When we model the wave function of the state roughly in terms of p orbitals, then what one expects is that we have pz orbitals and py orbitals in the upper and the lower part of the Dirac cone, but they are coupled via different phases. So there's a phase difference of pi between these orbitals. And this phase difference can be picked up by the circular dichroism due to the fact that our light electric field here in the z direction couples predominantly to the pz orbitals, and the light electric field along the y direction couples predominantly to these y orbitals. And due to this selectivity, we basically pick up the sign change between the py orbitals as or pz and py orbitals as a sign change in our circular dichroism. Then we can go a step further. We also managed to do spin-resolved ARPES experiments on these states. And indeed, we observe a spin polarization. So this is a cut in the momentum plane, roughly cutting this upper part of the Dirac state. And we observe this helical spin polarization that is also expected for these states. So this is yeah, more or less the best spectroscopic evidence that we can obtain that these are indeed topological surface states. Now moving to the 1 to 4 to the bismuth telluride terminated surfaces, we in particular wanted to understand the nature of this suppression of spectral weight here in the region of the Dirac point. And what we found is that the intensity distributions for these states here depend strongly on photon energy, and in particular at certain photon energies, for example here at 6 eV and 61 eV, we highlight certain parts of the band structure with high intensity, but going to other photon energies, such as here at roughly 80 eV, these previously intense regions are suppressed and other regions are suddenly higher in intensity. And this is related to a different orbital character of certain parts in the band structure, and the fact that regions with different orbital characters are excited predominantly at certain photon energies. So it's a quite subtle effect, but basically what it allows us to do now is to identify certain parts of the band structure as derived from the topological surface state. So this is seen here. This is a theoretical calculation of the surface spectral density projected on specific orbitals here. And we see that in this calculation, basically we see the same features as here in this ARPES data. And then other projections on here tellurium orbitals, they show now features that we observe here at this other photon energy. So we get a kind of one-to-one correspondence between the photon energy dependence here of different parts of the band structure and the orbital distribution here. And this allows us now to get a hint that indeed this upper part here and this lower part below this suppression of spectral weight both belong to the topological surface state, and that this reduced spectral weight, which is also seen here in the calculation, actually arises from hybridization with bulk states, which become suppressed due to the surface sensitivity in our experiments. So this also implies that the Dirac point here for this bismuth telluride termination is buried in the valence band continuum, unlike for the 1 to 4 terminated surface, where we have this Dirac point rather nicely in the gap. So this interpretation is further supported by spin-resolved calculations and also experiments. Here we look first on the calculation. What we see is that indeed this upper part here is strongly spin polarized, but also this lower part that is in the valence band continuum shows strong spin polarization, confirming the identification as the topological surface state. And we could also confirm this experimentally by observing spin polarization above and also below this region of suppressed spectral weight. So we come up with this model here where we have our topological surface state that strongly hybridizes with valence band bulk states, and this leads to spin polarized states above and below a region with reduced surface spectral weight. So this also implies that these bismuth telluride terminated surfaces are probably not useful for any transport experiments, because any potential gaps in the topological surface state would be buried in the bulk continuum and not accessible by transport, while for the 1 to 4 terminated surfaces looks more promising. Okay, we also studied higher N compounds, so additional quintuple layers inserted into the matrix, and basically the results look very similar. So these are now spectra for 1 to 4 terminated surfaces, one for the one we've already seen, 1 for 7, and this one is for 1, 6, 10. So we have a sequence of MBT, BT, BT, counting from the surface, and the ARPAS results look very similar. And here we have 3 different BT quintuple layered surfaces. One would be this one here is 1, 6, 10, where we have first BT, then MBT, and then again BT. And one trend that one observes is that this hybridization induced gap tends to become decreased for an increasing amount of bismuth telluride layers near the surface. And this is in line with the fact that when going towards bismuth telluride, this gap should actually vanish because it has not been observed for the pure bismuth telluride. One thing that we can also learn from this data is that the surface electronic structure is mainly determined really by the first van der Waals layer, meaning that the topological surface states are probably mostly localized in just one layer, and they're just really subtle changes due to the second and the third van der Waals layer. Okay. One interesting direction now in the field is to go towards the two-dimensional regime. Anna has already shown these results indicating that quantum anomalous Hall effect is possible to achieve in these types of materials. And one direction that we are following now in our lab is to realize the MBE growth of 1 to 4 and related compounds. This is just work in progress. We have already achieved to grow thicker 1 to 4 layers by co-deposition of bismuth telluride, manganese telluride, and tellurium on barium fluoride substrates, and started to characterize the samples. So in the TEM images, you can see the formation of this characteristic septuple layers, and magnetic characterization with XMLD shows antiferromagnetic order in these 1 to 4 films with a Néel temperature that seems to be in line with the one of the bulk compound. So we are now working to further optimize these films and to potentially also go into the direction of heterostructures or quantum size effects and so on. Okay, with this, I'm coming to the second part of my talk where I will present results on tantalum arsenide. So just a brief reminder on this compound. So this is in DFT at least, and the ARPAS data is in very good agreement with that, semi-metal. One can see that over large parts of the momentum space, this band structure is actually gapped, but there are some regions where these valence and conduction bands come very close to each other. And looking in more detail at these regions, one indeed sees in the calculations the formation of these Weil points. So one thing that is important is that this compound is non-centrosymmetric. So one can see already in the calculations that all these bands are slightly split, which is due to spin-orbit coupling, forming now spin-polarized bands. So what has not been shown yet in the experiment is that indeed these bands are actually spin-polarized. And I will show data in the following confirming this. One other question is about the Fermi arcs. So these are calculations of the of the surface electronic structure. And these are the projections of the bulk Weil points. And indeed, one can see in these calculations surface states that connect to these projected Weil points, but it's still not so clear whether these are really Fermi arcs. So one can see that actually we interpret these outer features here as Fermi arcs. One can see that surface features also extend beyond the projected Weil points, which you would not at least expect in an ideal model where these Fermi arcs become bulk states once they reach the Weil points. And in fact, in these early ARPAS papers, first reporting electronic structure results on these compounds, the identification of what specific features of Fermi arc has not been consistent. So there's still some open questions also regarding the surface electronic structure. So we studied this compound tantalum phosphide using synchrotron ARPAS, and this is now data in the VOV regime where we are rather surface sensitive. This is a comparison between ARPAS data along various high symmetry directions to DFT calculations. And if you take the time to compare all the different features, what you find out is that basically all the features that observed in the experimental data correspond to surface states. So really these experiments only probe surface states. We can now look in more detail at the predictions or at the potential Weil physics here. So these are now Fermi surface maps for the same sample. And here on the right, you can see as a guide a DFT calculation where we have these projected Weil points, basically at the separating the spoon-like outer features and this third feature here. So in the experimental data, we would expect them roughly here at these points. And now similarly as in the DFT calculation, also in the ARPAS data, there's no real, or at least no clear signature that these are really arcs that completely lose their intensity at these projected Weil points, but rather these states extend over the positions where we would expect the Weil points. However, what is interesting when you look at the dichroic signal, so this is the linear dichroism, basically the left-right asymmetry obtained for when you're using p-polarized light, what you see is that in both geometries, so along the kx direction and also along the ky direction, there are characteristic switches in this dichroism at the projected Weil points. So this is marked by these arrows here. When we move here along this contour, at the point where the Weil points in the bulk are located, the dichroism of the surface states suddenly switches. So there seems to be something definitely going on at these particular points in momentum space, and we can use DFT calculations to understand this in more detail. So what happens is that when you project your surface Fermi surface on particular orbitals, then you can actually also see this effect similarly as in the experiment. So when we project here on this on these types of orbitals, these features indeed look like Fermi arcs. So they really vanish once they pass these Weil points. And this other surface feature here has a completely different orbital character. So there's a sudden change in orbital character of these surface features once they pass this projected Weil points. And this is the reason why we can have these signatures here in spectroscopy. The sudden change in orbital character changes the matrix elements and leads to these effects in the dichroic signal. And we also see similar effects in the bare intensity in this measurement here for S-polarized light, where, for example, these spoon features or these arcs are completely suppressed along one direction, and then the other feature here in the other direction is completely suppressed. So there are consistently spectroscopic signatures at the projected Weil points. And we use DFT calculation to understand this behavior in more detail. So by looking at the localization in real space of these states, what we find is that these states that we here call alpha, so these outer surface states, they are very localized in the very first atomic layers, while the states become increasingly bulk delocalized when approaching this W2 point and going beyond this W2 point. So this would be these wave functions here in the middle, which clearly extend more into the bulk than the surface states here. So this is a possible explanation now that unlike in the ideal models where once the Fermi arc reaches the Weil points, you become fully delocalized in the bulk, get a pure bulk state. Rather, what we propose here is that these states become more delocalized, but still retain a sizable surface weight at least. So this would be something in surface science that would be called a surface resonance. And another confirmation for this interpretation is the fact that this feature beta here, which would be the surface resonance, has a very similar orbital character as the projected bulk Fermi surface. So one can interpret this in a way that the Fermi arcs kind of adopt their orbital character to the one of the bulk states and hybridize with these bulk states to form surface resonances once they reach the projected Weil points. Okay, now going towards probing the bulk states. So it has been shown already in these very nice early papers on these materials that one can use soft X-ray ARPAs to address the bulk states. And now our idea was to go beyond just probing the dispersion of the bulk states and to also probe the spin and potentially other properties of these bulk states. So this is a sketch here of the experiment when increasing the photon energy going towards the so-called soft X-ray regime, the final states become more bulk localized and allow for a higher bulk sensitivity of the experiment. And this is already seen here in this data set taken at 590 eV, where now completely different from the previous results, the spectra or the measured dispersion nicely matches the calculated bulk band dispersion. So there's no prominent sign, at least, of surface states. And in the calculations, we can see here that these states are indeed expected to be spin polarized. So this color code of the bands here corresponds to the spin polarization of these states. And so we took spin resolved data at certain points in momentum space, indicated here by these dashed lines. So these are the corresponding energy distribution curves with for spin up and spin down sensitivity. And one can see a certain shift between these two spectra, confirming that indeed these bands here are composed of two components with opposite spin polarization. And once we go from positive wave vectors to negative wave vectors, this spin polarization changes sign. So this is a demonstration that indeed also these bulk states are spin polarized, which is a prerequisite for the Weil physics. What is a little bit a problem is that, at least with our setup, we are not able to achieve sufficient momentum resolution to really study the details of the spin polarization, for example, close to the Weil points. So we were looking for another signal that is easier to obtain and still contains information about the character of the electronic states. And it turns out that the circular dichroism is again very useful here. So one interesting observation is that the inversion symmetry breaking not only induces a spin polarization of the electronic state, but it also gives rise to a finite orbital angular momentum of the states, which would not be possible in centrosymmetric systems. And one can see this here in the DFT calculation. So this is again a bulk band structure cut through the bulk band structure projected on the orbital angular momentum, and one can see that there are sizable orbital angular momentum components which show certain k dependence. And this is now, for comparison, the same experimental cut here, where the color code is the circular dichroism. And one can see, in fact, a very nice correspondence between the calculated orbital angular momentum and the circular dichroism. And this is probably not a coincidence, because there have been theoretical predictions saying that once the final state of our photoelectrons is close or approximately free electron-like, then indeed the circular dichroism signal should be related to the orbital angular momentum, in particular the component projected on the propagation direction of the light, which is also what we compare here in this comparison. So we can also look at this over entire K-space. So this is essentially here covering now the full Brillouin zone. And what we did here was to integrate over the entire valence band here, the first valence band. So each point in momentum space here gives some contribution, and we can compare the dichroism, the measured dichroism, to the calculation of the orbital angular momentum, and indeed there's a nice correspondence between both. So now one question is whether the orbital angular momentum that we can apparently address spectroscopically here is related to the Weil physics or to the Berry curvature. And at least under certain, in certain cases, there is indeed a relation between Berry curvature and the orbital angular momentum. So there's been a very nice theory paper recently suggesting that circular dichroism could be a probe in certain cases of the Berry curvature in momentum space, essentially based on this relation to orbital angular momentum. And this is what we looked at here now in more detail. Now we are zooming in a little bit on the region in momentum space where the Weil points are located. So these are indicated here, and we are considering a constant energy cut at an energy slightly off these Weil points. And we compare here the orbital angular momentum projection theoretically and the Berry curvature. And indeed the textures are compare quite well. So there seems to be some similarity at least. And also our circular dichroism seems to show these characteristic sign changes when moving along this contour. And one can theoretically go in even more detail and calculate the winding number of the orbital angular momentum across these Weil points, and also of the Berry curvature. For the Berry curvature, it's obvious that the winding is topologically non-trivial, but it turns out that the orbital angular momentum winding is also topologically non-trivial. So both quantities have the same winding number in this case, whereas theoretically it turns out that the spin is in fact topologically trivial in this compound here. So it's really the orbital degrees of freedom that carry the topological information in this particular compound. So we believe that with these experimental data, we get at least some experimental signatures that really the Bloch states close to the Weil points show this theoretically predicted non-trivial winding. Okay, and with this, I'd like to summarize. So I believe we have a very interesting new platform here to study interplay between magnetism and topology with various experimental probes. And in particular, we are now trying to go towards compounds with higher N, and Anna has already very nicely introduced also these antimony-based compounds, which could be interesting. And then I've shown that dichroism in ARPAS can yield signatures both of the surface and also of the bulk Weil physics in tantalum arsenide. Thank you.
Okay, thank you very much for this nice talk. Are there any questions? Yes, please go ahead.
Yes, I have a question about the small gap that you observe in the BT terminated.
It's still there.
Yes, that's right. Yes. You interpreted this gap due to the hybridization of the surface state with the bulk state. Could it be also just the hybridization of the top surface state of the BT with the bottom surface state of the BT?
No, this is impossible in this case because because these are single crystals. So we do not expect like this thin film coupling.
Oh, okay. Okay. And by the way, in this type of complex structures, do you think you see the electronic band structure of the whole material, or just you know, the few layers on top? Let's say if you have a BT terminated sample, you may see just the top BT layer and not too much of the bulk structure. Well,
yeah, definitely.
What do you think you see? Yeah.
Yeah, I believe in particular, for example, this gap that we see there.
Yeah.
So the suppression of spectral weight. This is kind of a signature of exactly this effect, because I believe, or well, I cannot really confirm it, but I believe that from all our data that there should be bulk states beyond, below this, or filling up this apparent gap, and it's just effect of the finite probing depth of the experiment that these states in the gap are not probed.
Okay.
It's also a bit yeah, it's a bit weird. It doesn't seem to be just a cross section effect, because for all photon energies we see this. So
okay.
So it really seems to be an effect of the mean free path. And yes, so in general, of course, we are, I think, only probing the first layer. The first van der Waals layer, if at all.
All right. Thank you very much.
Okay, another question. Did you see any effects from the anti-site disorder according to your ARPES data in manganese bismuth tellurium?
Not really, I would say. I wouldn't know really what to look for. So I think ARPES is not really the technique to address this. I would not be sure what to look for in the band structure. So that would be, one would have to start with very detailed theoretical modeling, how it affects the band structure, and then one could maybe look at it. What maybe is a little bit surprising is that one can obtain very, very sharp ARPES features, despite the fact that there's apparently a lot of disorder, at least of this anti-site character. Doesn't seem to be detrimental so much.
Okay. Another question is, can you further comment the connection between dichroism and Berry curvature?
Well, I think this is still work in progress. As I said, I think what is kind of established that under at least certain circumstances, the circular dichroism is related to the orbital angular momentum, which I think is quite convincingly just shown a posteriori, even by a comparison between these data sets, and also the fact that there is theory predicting that once you have a free electron final state, there should be some relation. And one thing I didn't mention is that at these high photon energies, we are 600 eV above the Fermi energy, and of course at some point one should approach the free electron limit. So it kind of makes sense. And then of course it's a question. So there's one more subtlety, actually, more of theoretical character. So what we found out in the study here is that what we probe here, or what we call orbital angular momentum, is basically really this atomic expectation value. So it's basically the wave function is the Bloch wave function is projected on spherical harmonics, and so it's more like an atomic orbital angular momentum. Whereas there's also an orbital angular momentum defined in Berry phase band structure theory. So these two are not identical. And so if that were the case, then there would really be a direct connection. I think at present, it's both theoretically and experimentally not yet clear under which conditions you have the further relation to the Berry curvature. I think this one still has to look at in very much detail for each system. And in this tantalum arsenide, there seems to be at least some correspondence, but it might be that it's lost in other systems.
Have you tried your measurements for different photon energies?
Sorry?
I mean, did you measure for different photon energies? Because we only saw data in the talk for, I think in the first part was 6 eV, and this one is,
yeah,
because different photon energies in circular dichroism change the sign.
Yeah, of course this can happen.
Yeah, but then
so
it doesn't match the very curvature, right?
Sorry?
But then there will be like, it would not match the orbital angular momentum calculations, right?
Yeah, so there are of course subtleties. So we have not. So what of course we of course tune the photon energy here in this case to just go into the KZ plane. So it's not so trivial as for the surface states, because you really have to also consider the out of plane component, and then you are at a certain photon energy at the Weil points, and then you would have to go to other photon energies, and it turned out that this is very tricky in this case. So I cannot show you, let's say, the same result at another Weil point, but what we have obtained now is more systematically data at different KZ values, and there this correspondence between dichroism and orbital angular momentum is still there. But I cannot exclude that at certain photon energies, of course, you get other effects. And so, of course, there's no one-to-one correspondence like energy and momentum conservation as for the band structures.
Okay, thanks. In manganese bismuth telluride, is it possible to control the localization of surface state by surface deposition of alkali metals or gas molecules?
Yeah, this would be actually an interesting experiment, but we have not tried that.
Okay.
I guess so, but
are there more questions? Guess not. There is Carmen Gomez. I mean, apparently so. Okay, Carmen Gomez, please, can you unmute yourself?
Hi, Henrik. Thank you for the talk. It was very nice. Very nice images or artist images. I would like to ask you, these samples after being drawn, do they have any capping to avoid oxidation while transferring the sample to the ARPES setup, or how do you do? Do you have a suitcase, vacuum suitcase?
No, I mean, most of the results I've shown are on the single crystals. So what we do there is that we actually cleave them in the UHV setup of the ARPES experiment. We are also doing experiments on MBE samples where this is always, of course, an issue. Okay. But they were not shown here.
Okay.
But yeah.
Okay, thank you very much.
Are there more questions? If not, okay, let's thank Henrik again and all the speakers of the session. And I think you can further ask more questions in these discussion rooms. Thank you.
Thank you.
So let me interrupt a little bit. So please come back to this Zoom meeting, to the Zoom webinar after the discussion session, so that Thanasis Dimolas will announce the next Topological Matter conference, which will be done next year in Greece. So let's go to the meetings now. Thank you.
Hi again.
Here. So I think that I see that people is coming back to the main meeting. So let me say just a few words to close the conference. First of all, I'd like to thank the speakers today and the speakers for 4 days. I think it's been wonderful. I've seen wonderful talks and very exciting results from skirmills, topological insulators, magnetic topological insulators, phononics, photonics, and there are many opportunities not only of each of these fields, but also between them, so interaction. So I think it is very important to have these kind of events and to persist in the future with these events. One of them that we are involved in organizing is a school that was mentioned by Peter Lodal the first day. Is a school on topological bosonics and electronics, combination of things. And it will be by the end of August, and this is free, anyone can log in. But then I don't want to talk much more. I want to give the talk to the screen to Thanasis Dimolas, which is co-chair of this conference, and will chair the next one in Greece, and hopefully we can be on site. So Thanasis, I give you the screen, you can share your slides.
Okay. Okay. Should be able to. It seems I cannot. Sorry. Okay. Okay. So say that I enjoyed very much this conference, and I want to thank all the audience who attended this conference, and also I would like to thank Sergio and his team. They did a wonderful job there, organizing everything in every detail very well, and it was a very good conference, very high level. All the talks were excellent, I would say, and I enjoyed it very much. And as Sergio said, I think at the beginning of the conference, this conference is supposed to be a dual conference, in the sense that we had the first part in which is this one here. It was planned to be at near Barcelona, but it was not possible, and we had it we had it online. And the second part was supposed to be in Greece, and we hope that we can do it on site, although it's not sure yet whether we will be able to do that, because there are some worrying signs about the epidemic. I hope everything will be straightened out until next year. Let's hope about that. But we plan to have an on-site conference, and this will be in the island of Spetses in Greece. This is near Athens, and it's going to be about mid of September. So September is a good month for Greece. We have quite mild weather, I would say, and it's a good time period to be in Greece. So, two words about the Spetses of Island. Actually, this is a small island. Yeah, this is a small island down here. And you can reach it from the Piraeus airport by speedboat, for example. you can go all the way down here to Spetses in about 2.5 hours. You can also reach it by bus, and you can get from the airport, following this way here, you can come to Porto Heli, and then you can take a water taxi, which is about 1.5 miles to go to Spetses. And we are offering airport service for free, included, I mean, in the fees. And buses can take you and bring you here in Spetses, and then they can take you from Spetses back to the airport. So a little bit about history. Just the origin of the current name actually seems to be, some theory says that it comes from Catalan, Genovese, and Venetian sailors, the Middle Ages. And it was called Isola di Specia, or Island of Spices. And of course, our Catalan friends and organizers, they should feel at home there when they come to Spetses. Also, there's an important role of these islands in the Greek Revolution 200 years ago. Actually, they supported the Greek Navy, and they provided privately owned ships in order to be able to for the Greeks to find for their independence. I would like to say that this is a car-free island. Only horse carriages and water taxis can take you to several places around the island. Of course, you can also hire a bicycle and go around the island. That's also a possibility, but you don't have cars in this island. This is quite good, actually. If you come to this island, you will enjoy that quite a lot. There are also a few places of interest. I'm pretty sure you'll not be bored when you are in this island. I plan to probably have an excursion to one or two places here, as I list in this slide. A few more pictures from the island. You can see it's quite beautiful, and I'm pretty sure you're going to enjoy. And this is some other pictures here of this island. And about the conference venue, it's called it's a college foundation, which basically operated as a model public school in these years here. Actually, it has stopped the operation as a school for some time now, and they basically do this kind of events like conferences and other events. It's actually the location is actually quite good. You can you have about 3 to 4 buildings here in a quite large area. Sorry, very close to the seaside, and also in the back you can probably see the city of Spetses is quite near. It's about 15 to 20 minutes. It also has quite some nice conference facilities, and also you can use this conference venue for accommodation. It has been renovated very recently. It's got about 38 rooms here, and there are going to be 20 more rooms in another building beginning of summer of 2022. And we hope that we can probably host around 50 people or even more in these rooms here, and quite good price. And also it's got several leisure rooms here, and it's got a library with some old version books. Well, I know that a lot of people from you have traveled to around the world in several luxury places. I was worried a little bit about the comfort that you can find there, and I was trying to find a good way to describe this venue as an accommodation place. And then I recalled some discussion I had with a colleague of mine who visited this place and stayed in this place about 5 or 10 years ago, and he liked it, and he described it in this way. It is, he said, it's a Spartan comfort. And this is exactly what it is. It's comfortable, but you should not feel that you are in a kind of very luxurious place. There are other places in hotels near this place that they can offer more luxury, but this is just about the comfort you need in order to have a good time in this place. A few more pictures about the venue. Here's another view of the venue. It also has an ancient amphitheater, and it's got a lot of green. And a few other pictures here about what you can find in this place. You can also have a football field here, which belongs to this. And when I saw that, the first thing it passed through my mind is that we can probably have a Tocha Skytop football match here. I'm not joking. I mean, we may try to arrange this. Although knowing that there will be a lot of good players from Barcelona in the Tocha team, I do not have very big doubts who is going to be the winner. And finally, I wanted to say that except from the accommodation inside the venue, you also have accommodation in several hotels around. The nearest one is about 350 meters. You can probably cover this distance in about, let's say, something more than 5 minutes. And also this hotel is about 15 to 20 minutes walk from, it's about it's about 10 minutes walk from the center of the Spetses town, the capital. And also you can find other hotels which are available in the town, and this could be only 15 to 20 minutes walk from the conference venue. So there are plenty of options to stay and enjoy your time in Spetses. With that, I would like to say that we'll be very pleased to welcome you to Spetses next year in September. And with that, I would like to thank you once more for attending this conference, and thank the organizer, Sergio Valenzuela, for the excellent job he did with this conference. I think he put the standards very high. So I know that I have a very difficult job to organize an equally a good conference in Greece next year. Sergio, back to you.
Thank you, Thanasis. I don't have much to say. Thank you for the very kind words, but with these pictures, we are already losing. So it will be wonderful, I'm sure. Hopefully, as you say, we can have the conference in Greece. Well, hopefully see you all, and keep an eye on the announcements. So thanks again. Not much more to say. Thanks, Thanasis.
Bye-bye.
Bye-bye. Let's keep in touch.